Again, good morning and welcome to week 4, the second part of it. Namely, we're going to be doing, first of all, finishing the topic because it's still, we're probably midway through it. We're not done with it. And then we're going to do applications. And I was waiting for this chapter to do the applications for it. We are in the year 2022. So as you might have guessed it, problem 22 from chapter 20 is going to be done today. Okay, so that's one thing. I'm not going to miss that. It's one thing to teach and it's another thing to have fun while teaching. So hopefully you guys also can benefit from that problem. So problem 2022, and then other problems I have in mind. One of them, which is a big problem, it's problem 47 from this chapter. And problem 47 is it's a real life application of this whole thing, namely for an engine for a Volkswagen Passat, which is a real vehicle with all the data being real, and you're going to be doing computations and things like that. So there are several problems that we're going to be touching on after we finish the lecture. In addition to the lab this time around, of course, all of the labs are simulations, is really heavy in terms of preparing you for the exam. So if you missed the lab this time around, lab 4 and even lab 3, you're going to struggle with the exam. So the lab has, of course, it's a lab, it's graded 25% of the grade and so on and so forth, but it helps you also prepare for the actual exam. So don't miss that. So that's basically what the whole thing is. So we are missing, what is it? 2 people now? No, 3. Okay. So hopefully they will join us before the class is over. Otherwise, hopefully the recording will be soon enough on YouTube so that you guys can go and pull it up, or maybe even on Canvas so that you can follow it. That's for the people who are not here, of course. So let me share the screen and pick up from where we left on Tuesday. Any questions before I move on so far? No? Okay, no big deal. So let me get my pen. Here it is. Let me summarize what we did so far, okay? So we said that Mr. Carnot in 1824 came up with the second law of thermodynamics. And the second law, the way he formulated is heat in a closed system, of course, does not flow from cold source with temperature Tc to a hot source, which is temperature Th, spontaneously on its own. The last thing in here is just to help you realize that there are heat pumps that could do that. A heat pump can actually transfer heat from a cold source to a hot source. But that requires work, as we saw last time, okay? This led him to the most efficient engine. And the most efficient engine turned out to have an efficiency of 1 minus Tc over T hot. So this is basically in a nutshell. Remember, this ratio is in Kelvin, okay? The temperatures are in Kelvin, so they are not in degrees Celsius. So do not tell me an engine that operates between 0 and 273 or 100 degrees Celsius, then you're going to be tempted to saying 1 minus 0 over 100. That is a no-no, because this 0 is actually 273, and this number is 373. So this is not in Celsius or any degrees, okay? It's only in Kelvin, that ratio. As a matter of fact, every time the temperature is involved, it's always in Kelvin. The only place where you're allowed to express it in other forms other than Kelvin when you're dealing with delta T. This you may use whatever you like, okay? Because, no, sorry, I'm sorry. Celsius, not Fahrenheit, because the ratio, the difference will have a factor of 5 over 9 or 9 over 5, depending on what the conversion you're going to be doing, if it's in Fahrenheit. So it's really not totally free. So only in degrees Celsius if you choose so, or Kelvin, okay? So that is really the thing I wanted to bring up to in here. So this is the most efficient engine. That's basically what he said. This efficiency is always less than 100%. That is because of this law. This is the second law of thermodynamics. Then we moved on, we defined the cycle. It turns out that that cycle has of course, the efficiency in general is defined as a desirable thing in this case, which is the work divided by the cost, which is Q hat. So this is in general, no matter what the engine is. Okay. I also defined this case where we define the coefficient of performance. For the cooling system, we said it's QC over the cost, which is the work now. Okay. If you really want to have for a heater, all you have to do is just add 1 to this number. So when I ask for the coefficients of performance, I really mean this one, QC over W. Because if I'm interested in the heater, all I have to do is just add 1 to that one. This number is always usually more than 1. The only reason why it cannot be sometimes probably closer to 1 is because probably the loss is due to the non-perfection, if you wish, in the heat pump. Okay, so that is why we say usually. When I say usually, 99.9% of the cases are going to be more than 100%. Okay, more than 1, I should say. Okay, and we computed it for a typical value, and it turned out to be about 7.8, which means that the value for the heater in that case is going to be 8.8, or they add 1 to it. Okay, this number is always less than 1. If this number is always less than this one, as a matter of fact, this E is at most can be EC, East of Carnot, and East of Carnot is always less than 1. So the more the efficiency of any engine at best can be that of Carnot. Okay, that's, if you wish, the second law also, and it's the thing. Then we talked about the work of Clausius, and he led to the expression for the entropy, and the way it's defined after he worked his long years, many years on this expression, he found it to be defined as this. So this is the infinitesimal value of the entropy. In other words, the change in the entropy over a finite region is going to be from whatever you start as to whatever you end up with, depending on the process of dq over t. Okay, so this is basically how the change of the entropy is.
What does delta S stand for?
I'm sorry?
What does delta S stand for?
The change in entropy. And this is, if you wish, the infinitesimal change in entropy. S stands for entropy. Okay. For the Carnot cycle, again, just a refresher. For the Carnot cycle, if you guys remember, it has an isothermal and it has an adiabatic. It has another isothermal compression and it has an adiabatic. Okay. So this two, Q is equal to 0, Q is equal to 0 because they have no heat in them. So these are the adiabats. And this is T is fixed, which is T hot in this case. And this is T is fixed, which is TC. Okay. Q turned out to be, when we computed it in here, is equal to minus W. And because, again, the temperature is fixed, delta U is 0 in this case for the isothermal. So it's going to be nRT, and this T is TH, ln of this volume over this volume. So usually we call this one point A, this one point B, this one point C, and this one point D. So technically, it's VD over VC, okay? That's what we found last time. And this is actually, we found it a long time ago. This Q, so this is going to be a positive value because VD is clearly greater than VC when I go this way, okay? This is what the engine is. Because this ratio is more than 1, therefore this whole value is positive. So this is your QH. Your QC, the heat that is dumped to the environment, is going to be QC, is going to be, again, minus W for this part of the process. And this is going to be VB over VA, the same values. And again, it's going to be positive in our TC now, because this is happening at the core temperature, ln of the final volume, which is VB, over the initial volume, which is VA. This number is clearly negative. Why? Because VB is less than VA. This volume is less than that volume. Therefore, this ratio is less than 1. And the ln of a fraction is always negative. So this ln in here ensures that this QC is negative. There is no Q in here. There is no Q in here. So if I want to find the W for this cycle, all I have to say is delta U for the overall. I start from A, I go to B, I go to C, I go to D, and back to A. This delta U is actually from A to B to C to D to A. This is a cycle. Must be 0, because my starting point is my ending point. My initial temperature is my final temperature. In other words, this is always NCV delta T. But T is TA minus TB, which is TC, by the way. This is TC, and this is TC. My point to start is the same, is my ending point. So that's why it's 0. Now, this is equal to Q overall, meaning from A to B to C to D to A. That's what I'm saying by all. Plus W from all, which is this area really. That's what that means. Well, if you Q from all, I have to add QC. That's the first thing, which is negative, by the way. And I have to add this Q, which is 0. And I have to add this Q hot, which is positive, by the way. Okay. And I have to add this Q from D to A, which is 0, plus my W, which is the network, is equal to 0. Clearly, from this expression in here, the entire work is going to be minus QH plus QC in parentheses. However, this number is positive. Why? Because QH is more than QC. Okay, this ln and this ln are the same value, and I made the argument for them using the relationship between this volume and this volume, and this temperature and that temperature, and this temperature and that temperature, and the volumes. And we made actually a big case for it last time. If you guys don't remember, I want you to go back into this argument in here where we actually showed that these ratios of the ln's are the same. That's why they cancel. These ln's turn out to be the same ln. The value, the numerical value of this log and the numerical value of this log are the same value. So at the end, this ratio, this ln, and this ln are the same numerical value, albeit the values in there are slightly. I mean, VD over VC, this compression and this expansion are the same rate in terms of the ratio of the volumes. Okay. Having said that, then the TC is less than TH, therefore QH is more than QC, algebraically, I mean, in the absolute value. Obviously, this is negative, the other one is positive. I can write it symbolically, this expression, the absolute value of the work, the negative is gone, the absolute value of QH, which is positive, doesn't matter if you put that way, minus a QC, it's the same thing. So that is basically the Carnot cycle. Does this ring a bell from last discussion that we did last time? Yes, no, maybe? This is the whole thing we did last time.
Yeah.
Okay, very good. So now let's continue this thing. And the first thing I thought we should start with, first of all, I want you to come back to this expression of Mr. Clausius. We're going to come back to it. Okay. Don't forget this expression. This is a very important one. Mr. Trump used to put a bunch of exclamation points when something is. I don't know how many I put in here. Okay. I think he still does. Anyway, so we're going to come back to that expression. But before we do that, let's calculate entropy for, you guessed it, isothermal. We did that already. For the isochoric, we're going to do that. For the isobaric, And one thing which is very easy, the adiabatic, this is 0. Why? Because it's 0 over T anyway. There is no heat during the adiabatic process. So delta S is equal to 0 here. That's why for the adiabatic, this process is actually is referred to as isentropic process. Process where the entropy doesn't change because it's going to be equal to 0. So for the adiabatic, it's an easy process. We did that. We can do that easily because it's 0 over T, no matter what T is. All granted that T is changing from T hot to TC. So T is changing. It's not fixed. But during the entire stage, Q is 0. So 0 over no matter what you divide it by, as long as it's not 0, it's going to give you 0. So for the adiabatic process, delta S is 0. So we don't have to worry about it. The isothermal, we already did that. For the isothermal, we found that Q is equal to nRT ln of the final volume over the initial volume. So in this, and it's fixed. It doesn't change. The temperature is fixed because it's isothermal. So delta S is going to be simply Q over T. And T cancels T, so it's nR ln of V final over V initial. So this is easy. So this one and that one is easy. This two require some work. I'm going to extend this isobaric and isochoric and add to them another process that we have seen, and that is for calorimetry. In this case, calorimetric, I don't know, processes. Okay, process, it's fine. Okay, for the isochoric process, dq, I'm going to go to the infinitism value. It's NCV dt. That's for this one, for the isochoric process. For the isobaric process, dq is NCP dt. For this process, dq, it's MC dt. All of them. The mass of the object times the specific heat times the change in temperature, where C is the specific heat. This is the lab 2, or lab 1 actually. This is where we did the specific heat in general. This is the basic one that was introduced in chemistry, and then we did that calorimetry, and we did, so this is basically the process. All of them involve a constant times dt, a constant times dt, and a constant times dt. This constant changes. For the isochoric process, it's NCV dt. For the isobaric process, it's NCP dt. For this process is going to be MCD dt. So in this case, delta S is going to be NCV, the integral from T initial to T final of dt over T. Remember, I have to divide this quantity by T. For this one, I'm going to say delta S is equal to NCP, the integral from the initial temperature to the final temperature of dt over T. So it's the same integral, with the exception of the coefficient being NCP for the isobaric process, and it's NCV for the isochoric process. The last one is in here, which is going to give me delta S, which is equal to, again, MC times the integral from the initial temperature to the final temperature of dt over T. And that too is the same. All of them involve that integral. And that integral is just the, what is the integral of dx over x again? You guys can remind me of that?
The natural log of x.
Beautiful. That's how it's supposed to be. Plus
arbitrary constant of c.
You don't mean the speed of light, do you?
No, I'm pretty sure.
So plus constant c, very good. But this is a bounded integral. So all of them, that c doesn't matter in this case, okay? And I know I made a big fuss over it last time because we needed it when we were doing the adiabatic process. We really had to work with it. So right now it doesn't matter. So in either case, delta S is going to be, open parentheses, the first one is going to be NCV ln of TF over TI. This one is going to be MCP ln of TF over TI. And this is going to be MC ln of TF over TI. where this is isochoric, this is isobaric, and this is for calorimetry, okay? What I mean by calorimetry, if you take a cup of coffee, for example, you put it outside, boiling hot, that is basically what we use. We use MC delta T and for the heat and so on and so forth. So we can find this thing. It's easy, okay? We can find this thing. For all of them, it's the same expression. The key word in here is this ratio is in Kelvin. I mean, the temperature is in Kelvin. They are not. I mean, in here, if you're going to find the Q by itself, you can use the Celsius. You can get away with it for the Q, but you cannot do it for delta S because it involves this ratio of the two temperatures, the initial temperature and the final temperature. It has to be in Kelvin, okay? And I cannot say this enough because even at this level, calc-based students, they sometimes make mistakes in the exams, which is really, really annoying. I mean, I don't have much hair left, but it makes you pull on it, okay? So please don't forget that this is in Kelvin, these ratios. I mean, it's probably safer to start working with Kelvin, forget about it, okay? This, the isothermal involves, it's NR, ln of the ratio of the volumes, okay? That's it, not the temperatures. The adiabatic is 0. So all four processes that we know of plus 1, we did them. Sounds easy, doesn't it, for delta S? Yes? No? Maybe?
Yes.
Yeah.
Okay, very good. Very good. So now, let me go back to that, to Mr. Trump in here when he put those exclamation points in here and talk about this expression. So remember ds is equal to dq for an infinitesimal process divided by t. This is the same symbols that Mr. Clausius has introduced for us. And we know from the first law that du is equal. This is an infinitesimal. This is not the overall. Just small change in temperature, small change in the whole process. This is equal to dq minus pdv. This is w if you wish. From this expression, it's clear that for this infinitesimal process, dq is du plus pdv. Okay? I'm going to sub for the entropy in here. The entropy, as I was saying, was a state function. This is was a state variable or state function. This is one of the things that Mr. Clausius argued. Because for closed process, if it's a reversible process, the delta S is equal to 0. Okay? Meaning that it only depends on that state and that state alone. And like Q and W, which are not state variables, they depend on the process. That's why instead of expressing the behavior of the system in terms of the energy, we actually can express it in terms of the entropy. So this is another way of expressing the entire state of the system. So this is what we're going to do now. So ds now becomes from this expression, I sub the value of dq as dt plus p over t dv. Or let me write it more conveniently. What is that eraser thing? I don't like this du here. I'm going to write it 1 over t du, just to keep, let me write it again. ds equals to 1 over t du plus p over t dv. It's the same thing, okay? I didn't like it over the numerator, that's all, okay? So this is the same thing now as saying that this function of the entropy is function of for n fixed. And we've been assuming that the number of moles is fixed all along, which means that n, which is actually equal to the number of moles times Avogadro's number, is fixed. So any process where the number of particles does not change, meaning the number of moles doesn't. And that's exactly what we've been dealing all along, okay? So do not tell me, okay, what happened if the number of moles changes? Well, that's not the case of at least this class in here. There is a coefficient called the mu, and that mu is actually called the chemical potential that comes into play, and that is the one that controls how many particles have entered either in a chemical reaction or changed their phase from liquid to gas or vice versa. So that is the coefficient. So we're not going to be dealing with that one. So we're only strictly focused on the cases where the number of moles or the number of particles, because they're only different by the number of Avogadro in this case, is fixed. So in this case, the entropy is a function of U and V, okay? Some function of U and V. Now, for those of you who did not take Calc 3, or even those who took Calc 3 or taking Calc 3, this is a review, if you wish, for some from multivariable functions, okay? If you're going to be an engineer, you may get away with it, but real life is multivariables, okay? Real life functions are not single variables. So real life is this stuff. So that's basically what it is. I'm going to introduce not probably how your calc teacher have introduced it, but let me give you just basically the idea behind it. It may be helpful even for those who took this class. I mean the calc class. So let me compute delta S. Where delta S, I meant by it, this function evaluated when U and V were intact before they changed. And these variables are independent variables. I mean, they can change on their own separately without impacting one another. In other words, there is no function in this case that relate these two. Otherwise, it becomes a single variable. Okay. So, and then compute the value later on when U went from U to U plus delta U. And independently, V went from V to V plus delta V, and subtract these two quantities. This is what I meant by the change in entropy over a finite delta U and delta V separately, independently. Those two are independent variables. So far, so good, everybody?
Yes.
Yes.
Very good. So this is just calculating the change in delta S between where these two variables change, okay? So let's subtract 0 from this expression. I'm going to subtract this number, which is 0, okay? So I'm going to subtract S evaluated at U and V plus delta V and add that same number as evaluated at U and V plus delta V. So far, I didn't do anything to this expression. All I'm doing in here is taking this expression and adding this value to it, which is identically 0 at this point. So delta S becomes, let me find the upper value, which is S evaluated at U plus delta U and V plus delta V minus this number, which is S evaluated at U and V plus delta V. So since I subtracted this number, I better add it quickly before I forget. So I'm going to add S evaluated at U and V plus delta V. And don't forget, I have to subtract this last number in here, which is S evaluated at U and V. Any objections on this last value of delta S? Is it the same? Look at this expression.
It's not the same, right? Because the second, or I don't know, I guess the third S of U is missing the plus delta U.
No.
Oh,
Look
actually,
at,
never
look,
mind. Just cancel each other out, so it is the same.
I subtracted that number and I added it quickly before I forget, okay? So it's like going to the bank, taking $10 and putting $10, depositing $10 at the same time. Would that change your account? No? So I subtracted $10 from my account, and in the same time, I added $10 to my account. It's the same transaction.
It's the same thing.
Yeah. So it did not change at all. So all I did was basically left the entire expression intact, which was S of U plus delta U and V plus delta V minus S of U V. So this did not change. Here, this operation is taking $10 and at the same time putting it back instantaneously. So it's not like taking the transaction and then coming back a day later and putting that $10 back. It's in the same time. So we're good. So the bank guy probably would look at it weird. What are you doing? But he should not object. I mean, that's your business. Good?
Yes.
Okay, so let me look at this expression, the first difference and the second difference separately. If I look at the first difference, the second term is the same. It's V plus delta V and V plus delta V. However, the first term has changed from U to U plus delta U. And then the second one in here, U is the same, but V has changed from V to V plus delta V. That's the trick behind it. That's the whole business why I did that, okay? So what I'm going to do is that's how I group them actually naturally here. And this is by itself. So what I'm going to do to each of these parentheses, I'm going to be multiplying it by 1. And I'm going to choose my 1 carefully. And my 1 for the first one is just delta U over delta U. For the first parentheses. For the second parenthesis, it's going to be delta V over delta V. At this point, it's also free operation. You can multiply by 1 anytime you like. Okay, nobody should object on it too. So the banker should not have a problem. So we tell him that this is $10 times 1, okay? So that he doesn't really tell you anything. So delta S will be this difference divided by delta U, which is S evaluated at U plus delta U and V plus delta V minus S evaluated at U and V plus delta V. And this whole thing is divided by delta U times delta U plus the second term now, which is also a big fraction, S evaluated at U and V plus delta V minus S evaluated at U and V over delta V times delta V. Okay, so far so good, everybody.
Yes.
Yeah.
Okay, this is the trick of calculus. This is where calculus comes into play. Let's take all the deltas go to 0. That means delta U going to 0, delta V going to 0, and delta S is going to also go to 0 in the same time. Everybody is going to go to 0. However, this ratio here, V doesn't change. It's the same V. It was V plus delta V on one side and V plus delta V on the other side, but U has changed. This is the definition of the derivative in calculus with respect to this variable, when the other one doesn't change. Obviously, the deltas actually will become du, these. So this will become a du, this will become a dv, and this will become a ds in that limit, just before they vanish, okay? So this is calculus now. Calculus, okay? So this is stuff now at this point we are in the realm of calculus when we do this last operation. That's why I started with the deltas. So the first term is going to be ds in here. It's going to be, look at this term. By definition, this is the derivative of the function s with respect to u when delta u go to 0. So the limit of this expression when delta u goes to 0, this is the derivative of s with respect to u, and the other variable is retained constant. That's all. Obviously, when delta v goes to 0, this doesn't matter because delta v becomes to 0. So this just become a v, and this just become a v. That's all. Because it doesn't matter in this ratio. What matters is the u that changed. So this becomes the partial derivative of the function s with respect to u, I mean to v. Oh, I'm sorry, with respect to u. When v is maintained constant times this d of u plus the derivative of the function s, again, for the same reasons. But however, with v now, u stayed the same. However, delta v changed now. So this number is becoming smaller and smaller, and this becomes smaller and smaller, and the ratio is by definition the derivative, the slope of the function at that point, okay? The slope of the function at that point, obviously this dv, delta v becomes a dv, that's all. So this becomes the ratio, this becomes the definition of the dv over when the function u is maintained, when the parameter u is maintained constant, when the variable u is maintained constant, times dv, okay? Do you guys understand this last step or not? This is by definition of the derivative. The only reason why we have these partials in here, this curly thing in here, is because the function s is not a single variable function. I mean, when you do that in regular calculus, basically, in the single variable functions, you find the function f of x plus delta x, and you subtract from it the function f of x, and you divide by delta x, and you multiply by delta x, and you say that this is delta f, and you take the limit when delta x goes to 0, delta f then goes to 0, but it becomes by definition the df, and this is the definition of the limit. The limit of this expression when delta x goes to 0 is by definition df over dx times dx, okay? So this is by definition this expression. Sounds good?
Yep.
Yes?
Yes.
Okay. Here is the thing, the mistake, some, at least people who do that, and this is a math thing, okay? This is not a ratio of df over dx. This is not divide df by dx, because it doesn't mean that. Don't simplify dx and dx in here. That's a mistake, because dx is infinitesimally small, which is practically 0. How are we going to divide 0 over 0? So it doesn't make sense. So in this case, this is just a definition. This is a symbol. Symbol of what? Of this operation. The limit of this expression over when this delta x goes to 0. As a matter of fact, in numerical calculations on a computer, this is what you do. You make this smaller and smaller, and then you take those ratios, and that is how you find derivative of data. You use this operation, okay? You have data, you don't have a function here to take its derivatives. So that's how you do it on a computer. That's how we actually do it practically. That's how we did it in the old days when people did not even have computers. They have a bunch of data and they wanted to find the slope. That's what they do. They take those ratios and divide them. So that's what you do in the lab actually too, okay? So this is actual thing. This is a symbolic representation of that operation. This is the same thing. This is actually the same stuff. This is the symbolic representation of that stuff. So those are symbols. There is nothing intrinsic or native to the df over dx than any of these expressions in here. Okay, having said that, let's compare this expression for ds and the new expression that I found for ds. There. So ds we found it to be, so let me put them one next to one another. So the first one, ds, we wrote it as 1 over t times du plus p over t times dv. Here we found that ds is actually the partial derivative of s with respect to u when v is maintained constant times du plus a partial derivative of s with respect to v when u is maintained constant times dv. Obviously, from this expression, the temperature and this ratio are the same. These are the same expression. This is using calculus if the function S depends on U and V, and this is from the thermodynamic relationships that we started with. So in here, it means that the entropy, at least the derivative of the entropy with respect to, is related to the temperature this way. So this is an important result. I mean, if you want to, you can compare the other two terms also, the partial derivative of the entropy with respect to volume, when the volume is changing, then in this case, it's going to be P over T, okay? I'm not interested in that expression right now, because I want to push this expression further, okay? Imagine a different argument that started to evolve. As a matter of fact, Mr. Clausius himself is the one who postulated it. And he thought that this entropy thing has to do with the way we organize molecules, okay, and put them together one next to one another, okay? And their energies, and that's how the entropy added. So he started to break that element all the way down to particles that make up the gas. Obviously, that at that time we didn't know about atoms or molecules, but that's basically his thinking about it. When Mr. Maxwell heard about that argument, because one of the criticism, as I mentioned before, was the fact that you're finding speeds for these particles that are of the same speed of sound. Meaning, if I take a smoke, for example, and I'm smoking, the minute I puff, why doesn't the smoke go the entire room quickly? Because the speed of sound is super high. And why doesn't the smoke fill the entire room? And Mr. Clausius argued maybe because these particles, they're colliding so fast with one another, they don't spread throughout the entire room, but they barely start to spread throughout. So that's his argument. Mr. Maxwell, when we heard about that one, developed that theory that we talked about in chapter 18, and he came up with the mean free path. And then it turns out that that's probably a good explanation for his arguments. Obviously, Mr. Maxwell was in Germany, was in England. Mr. Clausius was in Germany, and there was a gap in terms of communication, in terms of languages, especially when the next person, Mr. Maxwell, died in 1877, just after he published his Maxwell's equations of light that you saw in physics 2. Another German who was a student at that time, Boltzmann, took the ideas, both of them, from Clausius, actually from Maxwell, and he did not speak a single word of English. Actually, he had a dictionary translating things for him, and he had to learn English that way, trying to understand Maxwell's papers, and then he reworked the entire thing. And he came up with a symbol W for the probability of distributions for the different energies of those particles. Obviously, he was a believer in the particle theory, in the atomic theory, in the molecules, and at that time there were a lot of arguments against it because there was no evidence for it. The point being in here is, he came up with a 50-page paper, 50-page paper at that time, to describe the different arrangement of molecules to give you this entropy. Okay, so let me explain what I mean by that. Obviously, the energies for these different particles can be distributed over different values, okay? Now we know quantum mechanics, they're actually quantized. So how am I going to arrange these molecules, this n of them, which is a huge number, by the way, this n of them, albeit n is not changing. Where is the n when we talked about the entropy? We talked about the n, which is just the number of moles times the Avogadro's number. Here it is. This is a huge number, okay? So what I'm going to do then is the following. I'm going to assume that each and every one of them has only two values, face or head and tail, just like a coin, okay? And I'm asking, if I have only one coin, what are the chances of me getting heads? Obviously, if it's a fair coin, I can get either a head or a tail, that's it. So it's a 50% chance to get a head in this case. But if I have two coins, namely the number of particles start to change, I can have a head and a head, or a head and a tail, or a tail and a head, or a tail and a tail. If I have two coins and I flip them and they are fair coins, then in this case, what is the most probable state I'm going to find the two coins at? one of them can be head, the other one can be tail, is actually 2 times out of 4, which is 50% chance. Whereas finding both of them in heads is only 1 in 4, which is 25% chance. And 2 tails, in this case, is also 1 over 4, which is 25%. So my cones, if they are fair, and if there are 2 of them, and if I flip them, and they are basically fair coins, there is a good chance, a 50% chance of finding one of them in heads and the other one in tails. This is the most probable state. Probable state. Okay? That is if I have only 2 particles and they only are allowed to have two values of their energies. This is the most probable state at 50%. Granted that these 2 coins are fair, meaning that they can be equally well in any of the states. So this is the most probable state. Does everybody understand so far probability, the way that I'm describing it?
Yep.
Okay, it's simple enough. How about if I have 3 coins and I flip them? Here is the thing. I can have a head and a head and a head, a head and a head and a tail, a head and a tail and a head, or a head and a tail and a tail, or, I mean, this thing can become ridiculous very quickly, okay, and you will see. So, or a tail and a head and a head, or a tail and a head and a tail, or a tail and a tail and a head, or a tail and a tail and a tail. Okay, so those are the 3 particles basically that can allow to have 2 values, heads and tails, okay, provided that they are fair. Obviously, this is 1. This, to having 2 heads is I have 1 2 heads, I have 1 2 heads, I have 1 2 heads, so I actually have 3 2 heads, okay? 3 of 2 heads. So this is all 3 heads, okay? I have 1 of them. Having a single head is only, I have 1 single head in this case, I have 1 single head in this case, and I have 1 single head in this case. So there are actually 3 cases also where I can have 1 head. And there is 1 state where I cannot have no heads whatsoever. 0 heads. I mean, 1 state where I can have 0 heads. Okay. The total of this thing is 1 plus 3 plus 3 plus 1, that's 8. Actually, it's 2 times 2 times 2, which is 8. Okay. Those are the entire probabilities. I have 3, which is 3 over 8 chance to getting them either in this state or in this state. However, I have only 1 over 8 chance to getting them in all heads or no heads at all. So meaning that if I have 3 particles and if they only have 2 possible values, most likely I end up with either 2 heads or only a single head. Okay, that is the most probable state. Okay, let me stop sharing that screen now, and I'm going to share with you Mathematica because I cannot do the numbers past 3. It's ridiculously big. Okay, and if you know the permutations, did any one of you take the class in math called combinatorics? No, maybe. No,
I didn't.
Okay, yeah, so let's basically, this is exactly what this is how many ways you can choose, in this case, 2 states or a given state out of the number of 3, and this is given by the factorial function. Okay, so let me share with you. Let me get first of all Mathematica going and see how this numbers become. Okay, what is it? No, not mathematics. This is not good for mathematics. It has to be something that is capable of calculating factorials of 100 and 300 for me, because this is not going to be an easy thing. The book mentions the relationship that I'm trying to get at, but I'm going to quickly, let me go and change the format in here. I'm just getting this ready. So, and let's share the screen now. Okay, so first of all, I'm going to define n, and n really is the number of points that I have in this case, okay? N equals to 2. And if you know anything about Mathematica, when you do the semicolons, that you suppress the output, because I know n is equal to 2, okay? And I want to find, let me try to find the best way of describing this, okay? Let's get into the table. I want to form a table that is made up of the pairs I. I is basically the number of heads, okay? How many heads I'm going to end up with. And their actual probability, in this case, their number, how many ways of choosing I out of n, is given by the binomial factor, which is just something that you probably have seen actually in the distribution of the x plus a plus b to the power n. That's the coefficients of b, if you wish, okay? Or a, if you wish, doesn't matter which one, because they fluctuate with one another. Divided by, open parentheses, I factorial times n minus I factorial, and the whole thing close the parentheses. The reason why they fluctuate is because of this last expression. You have I and you have n minus I. So you're going to start values from I for I, and you're going to continue this one. So I want this pair, and I want it so that I starts from 0. So from no heads at all to all heads, okay, to n. And can I do it? Can I call this variable, first of all, something? Let's call it y equals to. Why is this doing that? Okay. So this is did I do something wrong in the calculation here? Okay, table form. No, something is not correct in here. Okay, sorry about that. Okay, let me remove this. This equal sign, I don't know why it's in here. As you can see. Okay, table form, open parentheses. I'm going to copy this expression because I think it's correct. I just want to reproduce a result that we did earlier. Okay, so we have no heads. We have no heads, one state, one value. Having a single head, at least, you have two ways, either head, tail, tail, head. Okay, having two heads, it's only one value. So this is exactly what I wanted to see. If I change n to 3, I should reproduce those results in there, okay? So if I change that, that's exactly the same result. I have 3 where I have one head, and I have 3 where I have two heads. The reason why I wanted to test it, I wanted to test it with what I know. If I have 4, then the probability will change more, okay? And I will tell you exactly where I'm going with this one. So if I have 4, obviously, having 2 heads and 2 tails, there are 6 ways of getting it. Having at least 1 head or 3 heads, there are 4 ways of combining 4 different particles, in this case, that have 2 possible values, heads and tails, into this one. Having no heads at all, meaning all tails, or having all 4 heads is basically 1 out of 16. If you add these numbers, they add up to 16. Or is it how many? No. 4 and 4, that's 8, and 6, 14, and 2 plus 16, yes. As a matter of fact, I can also compute n factorial. I mean, 2 to the power n. That's exactly what that value is. 2 to the power n, which is 16, okay? So yeah, so that's what these values are. Now, here is the deal. Imagine if I have 10 of them. 10 particles. This is not anywhere near Avogadro's number, by the way, okay? Then this expression will tell me the most probable state in this case what I can end up with, namely 5 heads. The system will most likely will be in any of these two, mainly here, if I do a test on it. It's not going to be possible for me to find it all with no heads or with all heads, okay? The most probable case in this case is going to be here. Obviously, in this case, it's 1024 ways of doing this, okay? I'm trying to bring an argument in here, and let me make a case for a large number. I'm going to use scientific form. And I'm going to have just a precision of 3. But I'm going to change the number now to 100 quickly, okay? If I have 100 particles, obviously this number is big, okay? If I have 100 particles, the most probable case is right around 50 of them. Here. It's not giving me the scientific representation. That's fine. Out of this many cases, this is only 100 particles. What's the purpose of this exercise, you're asking? If I do a test on my system, because it takes a long time, they're all equivalent, by the way. All of the coins are fair, so any of these ones are equivalent. But because there is more of this, the system will end up spending most of its time here than any of this, than in here or here. Because there are only 100 ways of getting one head. But there is this many of getting 50 heads, which I cannot even read the number, okay? So most likely we'll find the system in any of this state, probably at worst we'll get one of the nearby states. And this is if it has only 2 energies. So this is the foundations that Mr. Boltzmann started to make the case for his statistical arguments. If I take a macro state, if I take a system, for example, of a given energy, where is the back to it? Let me stop sharing this one in here. Hopefully you guys have seen the argument in here. And let me share my notes again. If I have a bunch of particles, and this is only 100 particles, they're not anywhere near Avogadro's number, okay? The most probable state where I'm going to find the gas in it, it's near where the system has the maximum value of these probabilities. He called it W, but I'm not going to use the letter W because I think for all practical purposes, we can use a W, which is the most, that's how we use, okay, probable state. This is where we're going to find the system at. If it has a given macro state. Macro state meaning it has a volume, it has an energy, it has all the other things, it has a number n of particles, which is critical for this whole thing. So this is the most probable state we're going to find it. The other ones are probably going to be less and less. And this is only 2 values. If it's 3 values for the energy, the problem becomes even more complicated. But the argument for it is, this is the rationale behind it. So the letter W is probability of the most probable macro state. How many ways can we arrange it in that way, in that organizations? Remember, I can have head and tail, or tail and head for the same state. Both of them have the same value, meaning one of them is head, the other one is tail. The thing with it is, the way that I arrange the particles, HT and TH, these are called microstates. In other words, this particle has this speed, the other particle has that speed. Now, if I flip them, because they're indistinguishable, this is another configuration, but it's the same value. It's the same macro state. It's the same values for my state of affairs for the whole thing. So he said the following, that a system will always evolve or will be found in the state with the most probability, in this case, W. So here is his argument for the following scenario. So W, first of all, is a function typically of U and V, and probably N, but N in all my practical cases, I am assuming it's fixed. So N is fixed, although I was changing it in Mathematica, but that's just for the purpose of exercise to show what happened in real scenarios, okay? That the system will be actually in the most probable value, not in all heads or all tails or some of them heads. And so it's going to be basically evenly. That's really where we're going to find it, okay? So N is fixed, as I was arguing earlier about the entropy, okay? So this is the probability function. This will be maximized at a maximum when the system settles down. If I do any test, that is the most probable value that I'm going to find. That is the most state that I'm going to find. The number of microstates that give me the macro state. That is, for the case of two coins, it's heads, tails, tails, heads, which is the same thing of having two heads. I mean, have less probable than this one, okay? Having said that, imagine the following case, okay? Imagine that you have two systems. System 1 and system 2. One has energy U1, volume V1, and the other one has energy U2 and volume V2. This is before we bring them in contact. Now we bring them in contact. This wall between them is immovable in such a way that V1 is fixed and V2 is fixed. So the volume does not change because this wall is separating them so that they don't move. So the volumes do not change. That's number one. The ends do not change. This is an impermeable wall. That means N1 is fixed and N2 is fixed. So that when we put them together, there is no way that some particles will somehow slip from one side to the other. That's not going to happen, okay? The only thing we're going to allow for is the energy to be exchanged, okay? So the only thing we're going to allow is might change. So energy exchange between the two systems, that's all. So we are in that realm of D with respect to U, okay? Now, if we do that, the total energy of the system, total energy, is simply U1 plus U2. Oops. That's all the system there is. This is our entire universe. There is no more energy. Energy cannot be created or destroyed. This is a conservation of energy. So this is how much we started with. At equilibrium, so this is fixed. The sum is fixed. Not each one is fixed. Each one can play whatever it wants to. There can be an exchange. One can gain more joules and the other one loses some joules, but at the end, their sum is fixed, okay? At the equilibrium, U1 can go to a new value now, U1 of equilibrium, and U2 can go to a new value, which is U2 of equilibrium. In other words, these two can change individually, but at the end of the day, their sum stays the same. So U total is still plus the new value for the other one, but it's still the same value. It didn't change. It's still the original one, okay? Now he said this is only possible because now the new big system has its own W, and that W has to also be maximized. So the new W must be maximum also, because this is true for any system of particles. Now I have two of them, but that's fine. So I started with W1. That's why I really don't like to use W, because I don't want to confuse it with work. So W in here is probability. In modern literature, in most books now, they use the letter omega. Okay. So that you know, okay. The book uses W, so I'm using W so that, and that's how originally, honestly, it was used by Boltzmann, because W stands for probability. There is a word in German that I don't even know how to say it that starts with a W for probability. Okay. So anyway, so the W must be maximum, meaning the probability of the entire system must be maximum. Now, since these two are independent systems, their probabilities are independent of one another. So in other words, if there are, for example, 2 ways of arranging system 1 and 3 ways of arranging system 2, then there is a total of 6 ways of arranging everything, because I can, for each one of these 2, I have 3 ways for this one. But I have 2 of them, 2 times 3 is 6. So in this case, the entire W is simply W1 times W2. That's how the probability need to be, because there are different ways of arranging system 1, different ways of arranging system 2. So the probability must be the product of the 2 probabilities, because these are 2 still independent systems. So here is the thing. W is W1 as a function of U1 and V1. V1 is fixed, by the way, times W2, which is a function of U2 and V2. This is maximum. That means its derivative, because it can depend on other variables, so I really have to use partial derivatives. Its derivative with respect to any of this, that's the only one that it changes, because the volumes are fixed. So in this process, the derivative with respect to either one of these variables, let's call it, I'm sorry, U1, must be equal to 0, because it's maximum. That's part of calculus. So that means the partial derivative of W1 with respect to U1 times W2 plus the partial derivative of W2 with respect to U1 times W1 must be equal to 0. This is just the derivative of the product of 2 functions. Okay. However, I have to be careful in here. I took the entire derivative with respect to U1. I have to use the chain rule in here to find the derivative with respect to U2, because W2 doesn't depend explicitly on W1, depends on W2. So I have to express the expression as W2 times the derivative of W1, which is just with respect to U1, which is just the first term, plus I'm going to write W1 in here times the derivative of W2 with respect to U2 times the derivative of U2 with respect to U1 equals to 0. I use the chain rule in here. However, I know what that value is. I know what du with respect to U1 is from this expression, because no matter how this changes, their sum is fixed. So in other words, d sub U2, so if I take this entire expression and take its derivative with respect to U1, so the derivative of U1 with respect to U1 is 1, plus the derivative of U2 with respect to U1 is equal to the derivative of the total energy, which is fixed, doesn't change, is 0. So that means du with respect to U1 is -1. So I'm going to take that expression and sub it in here. That is from the conservation of energy, that's all. I have U1 plus U2 is equal to 0, constant. That means that derivatives, if you add them up with respect to any of the variables, is 0. So, and since I'm taking the derivative with respect to U1, the derivative with respect to of U1 with respect to U1 is 1, and the derivative of U2 with respect to U1 is exactly what I need. So is equal to 0, because the total energy is fixed. And from here, I get a -1 for this derivative. So I'm going to plug it in here, and it just becomes a -1. So the last expression that I'm having in here is the derivative of W1 with respect to U1 times W2 minus W1 the derivative of W2 with respect to U2 is equal to 0. That is the condition of equilibrium in this case. Now, last step, divide the last expression by W1 times W2. Divide. Obviously, this W2 and this W2 cancel from the first term, and W1 from W1, the derivative of W1 with respect to U1 is equal to, I moved it to the other side, so it becomes equal to, I will be left with 1 over W1, 1 over W2, I'm sorry, because the W1 cancels. The derivative of W2 with respect to U2 is 0. This derivative is just the derivative of the natural log. This is the derivative of the ln of W1 with respect to U1. And this is the derivative of ln of W2 with respect to U2. That's all. Because I have dW1, so when you take the derivative of the ln, you drop the 1 over W, and then you multiply by the derivative of what you have left. So this is the derivative of ln of W. So here is the story then. When I bring two systems together, remember the zeroth law when we started with? When I bring two systems together and do not allow for change of volume and do not allow for change of particles, then they will reach a thermal equilibrium so that system 1's temperature and system 2's temperature are the same. That means systems 1 temperature, which is T1, must be equal to T2. That's exactly what that means. They reach thermal equilibrium. This is saying, though, as if 1 over T1 is equal to 1 over T2. That is the same thing, by the way. When you bring two systems together and their temperature is the same, all you have to do is just reverse that expression. It's the same thing. The 1 over temperature T1 and the 1 over temperature T2 is exactly that derivative that we argued for earlier. Where is it? Before we started this thing. This is delta S with respect to U at constant volume. And by the way, this whole process is as constant volume too. So these two derivatives, the volumes V1 is constant and the volume V2 is constant. And this says that delta S with respect to U1 at constant volume V1 is the same as delta S with respect to U2. S2, this is S1, this is system 2 at constant volume V2. These two expressions, this one, the one I'm looking at for the entropy, and the one that involves the natural log of this W is the same, except the denominator is the same with respect to the energies. The volumes are fixed in either of them. So what this suggests that this entropy is related to this natural log. The entropy is related to that natural log. And as a matter of fact, because the entropy has a unit, which is the unit of KB or R, so S must be some sort of a constant times ln of W, that's all. Or in the modern literature, we use a letter omega. S is equal to K ln of omega. Amar, what's that thing there when we integrate? This is just partials. This is just the differential form. So I have to add
Your arbitrary constant of C.
Constant. Okay, good. However, this constant is 0, and let me tell you why it is 0. There is a third law of thermodynamics that the only time we invoke it is in here. Third law of thermodynamics. Didn't I say that thermodynamics has 3 laws only? It has the second law that was written in 1824, more or less. Then the first law around 1850. Then after that, the 0th law. So when is the third law do you think came out? Does anybody have any idea? Does he have any suggestion?
After the 0th law.
It actually came before the second law.
I knew it.
This is the third law. The first time actually was mentioned by what's her name, Emily de Châtelet, who was a woman in France who did a lot of experiments. She formulated it, but because she was a woman, she did not even get notoriety. She wrote a whole book that Voltaire put it under his name. Okay. And then she published another separate book just because she was obsessed with that thing. And then later on, it was actually, what's his name? Clausius actually mentioned it also. And then actually it was formulated by Nernst way after the zeroth law. So it was put in formalism, if you wish, after the zeroth law, but it was first mentioned before any of these laws. So the third law of thermodynamics said the following by Nernst, that when the temperature drops to 0 Kelvin, which is impossible now we know. Okay. At that point, there is only one possible state, W, because all the particles drop to no motion whatsoever. So you can only find them in only one microstate. You cannot swap them. The only reason why you can swap them is because of thermal agitation, because C is not 0. So they are fixed now, transfixed. So there is only one microstate possible only. And at that point, then the system is completely ordered. That means the entropy must be equal to 0. So if we apply this and we put W equals to 1, the natural log of 1 is 0. And the constant must be 0 then, because I will have 0 equals to 0 plus constant. Okay, that's why the constant is 0 now, because of the third law of thermodynamics. Okay. So this is basically an argument that was made for way before this whole thing was argued. And then at the end, basically to hold, to help us find this constant. So now this is a value for the entropy. You can write it with a W or omega, okay? You can find it in any of the books. K must be a constant that that depends on the properties of particles. And Mr. actually Planck is the one who put this formula first of all in writing. Mr. Boltzmann put it first of all, mentioned it briefly, and Mr. Planck put it explicitly in this way. Okay, the constant K must be of the same order of magnitude of KB. As a matter of fact, it's KB. Joules per Kelvin. This is the value that actually we were able to find the electric charge. Well, it's one of the fundamental units. So this KB that we were talking all along about it, it's the same constant. This is really an important law. Now, if you wish, another way of formulating the second law is a system evolved so that the probability of the microstates, for the number of microstates, is maximum. And the entropy can never be 0. It's only 0 at T equal to 0 Kelvin, that's it. So the entropy always will increase. So you can think of this one as another reformulation of the second law. So W is always increasing, or omega is always increasing. Omega is a huge number. And remember, just for the two states, it involves the factorial of n factorial. Imagine if you have an Avogadro's number, it's going to involve n factorial big time. Calculations become ridiculously hard. So you really have to do all kinds of calculations for it. I mean, there is a problem that we're going to be doing, and that problem actually gives you a simple way of finding that factorial. Okay, so that is one way of doing it. If you go to Vienna, okay, people go to Vienna for all kinds of reasons. Probably the most likely reason you go to is probably the coffee, because Vienna is known for its coffee, or for opera theaters and things like that. Let me try to go to Google now, or actually use Bing, it's the same thing. And let me share with you the screen, as if we are in Vienna. We're not. What is the my share? Okay, so Vienna Cemetery, or Boltzmann tomb. And let's look at images. This is his tomb now in Vienna. Can you guys see what's written on his tomb? Let me bring it up close. You guys see it or not?
Is it the 5 equals K log W?
Yeah, the S thing.
Yeah, S, the entropy. That is what's written on his tomb, because he committed suicide at the end because he had depressions, and his wife, who was a very good, smart person, and she actually, Henriette, her name, she wanted to study physics, but she was banned because she was a woman. Women were not allowed to go to a university and study math and physics, so it was kind of a thing. So he urged her to to actually go to sue them, and she got a place to go to. She did all of his basically experiments, by the way. And so is the wife of Maxwell too. At some point he was asked about some data, and he told them, unfortunately, I cannot provide the data for you because my wife is busy. So when she's done with the collecting, she's going to collect data and send it to you. So just to show you what was going on at that time. It's really at different times. So his wife's Ostrich tomb is in here. I think his son also was a what is it, scientist. Anyway, if you go to there are all kinds of famous graves in there, Beethoven and Mozart and all kinds of things. So after he died, and after people recognized how much he did really for science, an elderman brought his tomb and put it in this main cemetery where everybody's buried. All the famous people are buried from Austria, buried in that place. So, and that is his tomb, and that is a law that you learned about. Again, I tried to use the letter W because it was used originally, but the letter omega, capital Omega, is actually used also to represent the same thing. So if you see it in books and things like that, do not get alarmed. It's the same thing. And it was first put by Mr. Planck himself, okay? The actual formula itself, it was put by him, but he stated that this is due to Mr. Boltzmann because of the fact that in his 50-page paper, you can see there that he was mentioning the natural log as basically corresponding to the entropy, but he didn't put that constant there. It was Planck that put it, and it's not known as Planck's constant, it's known as Boltzmann constant. And because there is another constant that we're going to discover soon, that's called Planck's constant, which is actually an important constant too of nature. So again, he committed suicide. One of the things that people did not really they didn't like about him is the fact that he was promoting the idea of the atomic theory and the fact that the molecules fill the air. And a lot of people did not believe that. And he had a lot of enemies in Germany. He actually had to leave Germany because of that. And then one of his, I forgot the names, but he came back to Germany. He was, of course, living in Germany and not Austria at that time. And the point being in here is that he tried to argue for it, but at the end, the depression took the best of him and he died. And his wife actually did a lot of work for him and actually helped propagate his ideas, and other scientists later on, including one of the people who was opposing him, actually. Planck himself did not like this whole business of probability. And I know we are a minute outside of the scope of this one. And one of the arguments that was made against this whole probability business, because it's historical context and it's a good idea to know it, is that Planck himself, he didn't believe in this until he was forced to. And we will see later on that why he was forced to, actually. And he won the Nobel Prize for doing something he didn't like. The point being in here is that this whole probability idea, before he died, Mr. Maxwell gave an analogy of all of this. If you take a cup of water filled with water and you go to the ocean outside and you dump that cup of water in the ocean and you come back later, it doesn't matter how later, a minute later, 5 minutes later, a day later, a month later, a year later, there is a non-zero probability that if you take an empty cup, that same empty cup, and you scoop it out of the ocean, you will end up with the same cup that you threw a long time ago before. Does this sound improbable? Yes, it does. I mean, it's the probability for it is almost zero. It is practically zero, but it's there. It's finite. This is one of the reasons that people hated this whole business of probability and W and things like that, including Planck himself. He didn't believe that there is something the entropy is so fundamental to nature that how come it does this to us? It's really, it doesn't make sense. Yet there is a non-zero probability if you come a month later, you're going to scoop the same water out of the ocean. That is basically how Maxwell put it at that time. And that is really how this whole thing was going. Isn't this fun? Yes, no? Okay, so we're gonna take a break now for about 10, maybe we will meet around 9:45. Okay, right now it's 9:30, 9:28 to be exact. So around 9:45, we'll guys go and drink and take a break. I'm not going to close the session, so please do not leave. I'm going to just pause the recording so that when we meet again, we'll resume the recording. Sounds good? Because we still have a lot of things to do. We still have problems, and we still have also actually important cycles that we need to mention too, and we have a lab. Okay. So see you guys in a few minutes, okay? Again, welcome to the second session of today, which is really the lab portion. As I was saying before, we only have about 11 chapters in this class. This is the 4th chapter. We still have 7 more chapters. The first exam is going to be covering chapters 17, 18, 19, and 20. And then chapter 37 will be introduced next week. On the 28th, which is the last day of the month, is it? February. No. On the 24th, which is not this coming Thursday, but the Thursday after, will be our first exam. Okay, so this exam will be covering these chapters. So again, the exam is going to be in the morning during the same time when the class is going to be held. We will not have a live Zoom session, so you can the exam will be open and you guys can go and take the exam and submit it on Canvas. So that's the format for the exam. This chapter is almost done. We're going to do applications for it. And then, as I was saying, the lab is important. So we're going to do the lab nonetheless today. It's very important. And we probably are going to do next week, we're going to divide the week into 2. Tuesday, we're going to introduce chapter 37. Okay. And then Thursday, we probably are going to continue with the applications from this unit and overall, at least, and then see how it goes. If we're good enough, we think that we're ready for the exam, then we probably are going to have the lab on that day. If not, then the lab for the relativity is going to be postponed, and we finish this stuff in here. Then on the 22nd, we will continue the discussion on chapter 37. Does this sound like it's a good plan for those of you who are here? I know most of you are.
Yeah.
Okay, so this is basically where we are right now. There are 3 cycles that are important. 2 of them actually can find them in the applications. One of them you hardly are going to find in the application, but it's worth mentioning because it's a cycle that you will find in your application, in your daily experience. The 3 cycles are the Otto cycle, and this is problem 47 from the book, okay, which is on page 675. So we're going to go through that problem anyway. And then the diesel engine or diesel cycle. I mean, you can have application, it's really not hard to do, but it's lengthy in terms of the calculations, and we'll go through it anyway. We'll explain what the process looked like, or at least what the cycle looked like. And then the other cycle that you're going to see is actually in the book also, and actually I did a demo for it in the video before the first video of it's on top of the videos of this week. So hopefully you have seen it actually in action. And then there is a problem on the book on page 676, and that problem is 56. And that is the Stirling engine or the Stirling cycle. Those are the cycles worth remembering, other than the bunch of cycles that you're going to have in the lab, about 10 of them. and other problems that we're going to pick up, which are kind of hypothetical, if you wish. A lot of them are hypothetical cycles. Okay, so I promise to do problem 2022 because we are in the year 2022. And because it's a good problem also that is worth knowing in terms of getting into the exams and so on and so forth. Next year, I probably will do, if I'm teaching this class, problem 2023, and you guessed it, the year after 2024 and so on and so forth. I could not do it before that, so I'm having fun, I guess. Anyway, problem 47. So hopefully you guys have the book open, and we're going to go through the Otto cycle. We're going through this problem. So let me share the screen. Where is the pen? Here it is. So the problem we're doing right now is from the book. (2047), and that problem is on page 675. And hopefully you guys are ready also to follow the reasoning. Before I do that, this problem relies on the Otto cycle, and it's for a VW Passat vehicle that is common in everyday applications. So that's what the problem is, and it uses the Otto cycle. And this is Mr. Otto who introduced this cycle, and it's used in cars, light vehicles, basically. It uses gasoline. Let me see if I have an animation in here of this cycle. Let me see if I can find it in here in my stuff in here, because I thought I downloaded this thing in here. I downloaded it from my Wikipedia. If not, maybe we can find it in there. No, it's a nice animation in there. Okay, it gives you the entire four-stroke cycle of the engine. So basically, what you have in the normal engine, if you wish, your car's engine. Okay, let me show you the. It has basically the cylinder, the piston, and the different kinds of valves, the two valves, the intake valve and the exhaust valve. And also it has the, if you look at the book, it's on page 647. So this is basically how a typical cylinder would look like. So I'm going to try to draw it as best as I can. So there is an intake, and there is a cylinder in here. I mean, piston, a cylinder, and in the cylinder there is a moving piston. So the piston goes up and down, and attached to it there is the connecting rod and to the crankshaft. So there is a rod that is attached to this one, and there is a crankshaft that turns, and that's the one that really makes the whole vehicle go on and up. So in here there is a spark plug. If the gas is completely compressed, the spark plug, the gap between it shrinks just enough for it to ignite. When it ignites, it triggers a chemical reaction. So the intake valve is here, and this is the exhaust valve. So the intake valve will open, take the gas in. Once the gas in, it's compressed. The spark plug basically triggers the fire, the combustion. The intake has two things. It has the combination of the fuel and air, which is mainly at gamma equals to 1.4 for all practical applications. And then once it's compressed, and it's going to push the piston down, and the rod will push the crankshaft, and the crankshaft starts to turn. So this is basically how the mechanics of the car is. So this is your cylinder, this is your piston, this is the when the gas is being expelled, this valve will open actually, and then the gas will go through the exhaust. So there is the exhaust in here, and this is the intake. It comes from your fuel injectors, from your fuel injectors. So this is the intake, And in the intake, there is actually another thing that is the oxygen sensor. The oxygen sensor determine how much air needs to go in addition to the fuel that comes in from the fuel injectors. And both of them, the combination will go inside to be combined. If you have too much air inside the pipeline, inside the exhaust pipes, sometimes the oxygen sensor would think that there is more air, so it's going to instruct the fuel injector to send more fuels so that the ratio stays the same. And that probably, if it's not correct, it's going to put stresses on your piston, which can damage the piston in here that is going up and down, or the entire cylinder. Okay, so this is a cylinder. V4 has 4 cylinders of this type, V6, 6, and V8, and so on and so forth. So this is a typical, basically, an engine, and this is how the cycle looks like on a PV diagram. The biggest question that you might ask is, what happened to N? Didn't you say that we're saying N is fixed? For all practical purposes, when these 2 valves are closed, yes, N is fixed. So during the intake, I'm taking and I'm getting out so that N stays the same. So for all practical purposes, I'm assuming N is fixed, okay? And that's how good engine should work. So this is your V axis. This is your Y axis, which is your pressure P. We start usually from this stage. This is the volume. This is position A, and this is pressure PA. Typically, this is around the atmospheric pressure. Okay, PA is around the atmospheric pressure. And we go through compression in this case, that is adiabatic, Q equal to 0. Once we reach the stage B, I should say, this is point B, the volume is VB. Then we're going to increase at constant volume. So this stage of the cycle is actually at constant volume. This is the heating up. This is when the spark plug is pushed all the way. This stage, a chemical reaction will start and trigger the high temperature that is reached in here. So at that point, point C reaches a point PC. This is PB, of course. The volume is the same. So this is an isochoric process. This is the intake of the heat. This is QH when it comes into play. Then there is another adiabatic expansion. This is where that stroke of the engine that pushes against the crankshaft. That's really where the power of the engine is. The harder it pushes on it, the faster the car goes. The faster crankshaft, depending on what gear you are in, the car can go into higher and higher speeds. Okay, for an automatic, it does it on its own. For you, you have to put the proper gear for a manual. So this is the point where the volume expands all the way to the maximum. Okay, so this is VA, and in the same time, this is my starting point. This is actually VD also. When it's fully compressed, that is what I meant by the point VB or the point VC. When it's fully pressed all the way. The stroke is this distance that the piston travels up and down. The ratio of this volume, the entire volume, minus this one, the ratio of VA over VB is called the compression rate. Okay. If you're in the business of making cars or engines, that's something you have to pay attention to. How far the piston will move versus how far it's going to be compressed. That's all. Now, that ratio is a fixed value. It's R. It's the manufacturer that gives you that value. You don't monkey around with it. So that's fixed. You don't play with it. By construction, basically, by design. The engineers who design that, they give you that one. And as I was saying, gamma is also, for a typical engine, is air, which is 1.4, which means that CV is equal to 5 over 2R. Remember, R is 3.14. So times 5 and divided by 2, 5 times 8 is about 40 point something something, divided by 2, which is going to be about 20 point something. Okay, so that is the value of CV. Obviously, it's going to be in joules per Kelvin. Okay, so those are facts. They don't change for everyday engines. Okay, the only thing the engineer in here is going to do is put that value R depending on what they wanted. Okay, they want a big engine that has a big stroke, they make this very deep. Okay, but then they have to make this one very sturdy because it's going to be very tremendous pressures in here. You have to be careful with it. So that is basically what the whole thing. So there are, this one is Q equal to 0, by the way, and here is the exhaust. Here is where the gas is leaving in this case. This is QC. This is dumped to the environment until it cools down. It comes back to the atmospheric pressure again. So this is the whole Otto engine. Let me go back into my drawing tool in here and define. This is my TH. This is the hottest temperature possible. This is my TH. There is a lower temperature. Let's call it TC. This is my TC. Those are the isothermals. Isothermals are different than the adiabatics. Okay, and there are two intermediary values for the temperature actually in this cycle. There is this value, which is TB, and there is this value, which is TD. Okay, so that is basically what this whole cycle is, what this whole engine is, described in terms of the cycle. Okay, let's calculate the efficiency of this engine. Obviously, the efficiency of this engine should be straightforward from the theory. The efficiency of this engine, which is the Otto engine, is going to be the work that the engine does divided by the cost, which is QH. Well, QH is simply equal to NCV delta T. Because remember, this process from here to here, from B to C, is an isochoric process. Okay, so this can be written as NCV times TC minus TB. The temperature at point C, which is TH, I wrote it in here, minus the temperature at point B, TB. Okay. QC is going to be NCV delta T. And that too is NCV, because that too is actually an isochoric process, constant volume. The final temperature is actually TA, which is usually a room temperature, around 300 Kelvin. That's the exhaust, minus TD, the temperature at the end of the adiabatic process, in this case, the power stroke. Okay, the end of that cycle. So that, but obviously this number is negative. You can clearly see from the graph it's negative because the temperature TA, the green one, is less than the temperature TD, the blue one. So it's definitely less. So this is a negative. That's exhaust. It has to be negative. It has to be energy leaving the system. It has to be that way. Okay, there is no heat in this stage. There is no heat in this stage because those are adiabats. So in this case, the work W net must be equal to, in absolute value, QH minus QC for the entire cycle. That's it. Or if you wish, it's going to be minus QH plus QC. It's going to be the same value. Okay, except it's going to be negative in this case because QH is positive and QC is negative, but that difference is actually a negative. I mean, a positive times negative is going to be negative because that's the work done by the engine. So it has to be negative. Okay, although in the book they take the other way, the other convention. Okay, so now having said that, what is the efficiency of this engine? It's this W divided by QH. So E for this Otto cycle, it is W, which is NCV times TC minus TB, that's QH, minus QC. So because this is a negative number, the way it's written like that, like this one, so I'm gonna take the absolute value, I have to do TA minus TD minus 3A. So it's minus NCV TD minus TA divided by Q hot, which is NCV times TC minus TB. Obviously, NCV drops. So it doesn't matter even what kind of fuel we're using, even if it's helium. I mean, helium is not a fuel, so it's not going to burn. Okay. So if we somehow do something to it, okay. So, I mean, the mixture, which is really the main thing for the fuel. I didn't mean the fuel. So the mixture, in this case, you could theoretically you could put fuel. You could put helium there. Anyway, E naught is going, obviously TC minus TB over TC minus TB is 1. Okay. Minus TD minus TA over TC minus TB. That's the whole thing in here for this. The difference in temperature here in this stage over the difference in temperature over this stage. Take that ratio, subtract it from 1, and you get the efficiency of this engine. Now, I know that TD and TC are related to one another. TD and TC are related to one another by the adiabatic gas law. So we know that TC times VC to the power gamma minus 1 equal to TD times VD to the power gamma minus 1. Similarly, I know that TA, because they are adiabatic processes, times VA to the power gamma minus 1 is equal to TB times VB to the power gamma minus 1. In other words, this temperature times this volume to the power gamma minus 1 is this temperature, TB, times this volume to the power gamma minus 1. And this temperature, TD, times this volume to the power gamma minus 1 is the same thing as this temperature times VD to the power gamma, times this volume to the power gamma minus 1. So that's basically what I'm writing in here. This is the adiabatic processes. So I can write TD in terms of TC, and I can write TA in terms of TB. So TD from this expression is equal to TC times VC over VD to the power gamma minus 1. And TB, or I'm sorry, I need TA, not TB. Because I need to express somehow the numerator, which has TD and TA, in terms of the denominator, which has TC and TB. So I already did TD, so all I need now is the TA. So TA now, from the second equation, is TB times VB over VA to the power gamma minus 1. However, the ratio of VC, what is it? VC over VD, VC over VD, VC, here is VC, and here is VD. VC is 1 over R VD. It's the same volume. And the same thing, VB over VA is 1 over R, according to this. So that's the compression rate, the inverse of the compression rate. So this is nothing but VC over VD, it's nothing but TC over R to the power gamma minus 1, because that's the inverse of R. And the same thing in here. This is TB over R to the power gamma minus 1, because that is VB over VA, the smaller volume over the bigger volume. And that is also the smaller volume over the bigger volume. So these temperatures are related to one another using these expressions in here. So let's go back to this efficiency and put the values in here for this T for the numerator. So E naught will become 1 minus, first of all, the denominator, I have TC minus TB. That is a denominator. The numerator, I have TD. TD is TC over R over to the power gamma minus 1 minus TA, and TA is TB over R to the power gamma minus 1. R to the power gamma minus 1 is the same factor for both of them, and it's the same denominator. So this comes out, and it will be left with TC minus TB over TC minus TB. But don't forget that R over 1 gamma. So everything will be simplified, and you will end up with 1 minus 1 over R to the power gamma minus 1. So this is the efficiency of this engine. That's it. So a normal engine has this efficiency. It has to do with the compression rate. So to make this one as high as possible, almost 100%, make R as big as possible. Make the cylinder as tall as possible. That's it. So if you're an engineer, that's all the secret behind making a more powerful engine. More efficient engine, I should say. Okay? Using this cycle. The problem with this is the following. If you really make it the compression rate that high, in other words, make this very long cylinder, the problem is this relationship in here. This one stays at room temperature because that's how the engine would work. So this stays at room temperature and normal pressure, but this one has to increase very high. The temperature becomes so high now that the fuel will ignite on its own. You don't have to wait because the temperature is so high when you compress it before you even reach that compression rate where it needs to ignite. Using the spark plug, it's going to ignite on its own. And that is the knock you hear in the engine. That's the pre-ignition, what is it? It's preemptive ignition, and you don't want that. That's actually an undesirable effect, okay? You don't have the proper mixture to begin with. You don't have enough fuel to combine with the oxygen, and the oxygen, the engine will be under a lot of stress. So there is a technical limitation, if you wish, to that. And the other thing also why this efficiency is not that high anyway, this is actually an upper theoretical limit, is because there are heat losses to the walls, and there are all kinds of stresses in here and there. So there are technical limitations on that efficiency of this Otto engine. Okay. As a matter of fact, the next cycle takes advantage of that. Okay. And let me draw it quickly, and we're going to talk about it just this much. Okay. So this is the V, this is the P, at least at this point. Again, this cycle starts from the point A, goes through an adiabatic. From here, it's not going to go through an isothermal. Instead, it's going to go through an isobaric process. And then it's going to go through another adiabatic. So both of these are Q equal to 0. And then it's going to go through an isoquatic process. So this is actually the diesel engine. If you work out the details of this one, which is not really that hard, this is your QH, which is NCP delta T. Where again, this is point A, this is point B, this is point C, and this is point D. Where delta T is TC minus TB, similar to the first one. And the other one, the exhaust, is going to be NCV delta C, similar fashion. Q is 0 for these two cycles, so you can find the W in this case, and you can find the efficiency, except now there is this intermediary volume, VC, that sits between the compression rate, okay? That is going to determine, if you wish, how good this engine is, because that is where TH is going to be located, okay? So now the problem with this one, this is the diesel engine, as I was saying, is that you can make R very big. Do not use spark plugs. When it's compressing, that's when it ignites. So for a diesel engine, you don't need spark plugs. Okay? And the efficiency of this one is actually greater than the efficiency of the Otto cycle. The engines are big. That's why you have to, because for heavy machinery, you can use that one. Does the diesel engine make sense to you guys as compared to the Otto cycle?
Yes.
Okay. Is everybody else following also?
Yes.
Okay, very good. So the difference between them is just for that, the last stroke before the power stroke, and that is the compression really that ignites the fuel. The first one relies, because it doesn't have high temperatures, relies on that spark plug to kick the whole thing and get it going. This one reaches high compression, extremely high temperature is going to ignite on its own, okay? So that's really the key difference in here. And that's why a diesel engine for big machinery is more efficient and you have to use it. If you use a small engine like this one, you're gonna need a lot of fuel to get it going, okay? That's really the big difference between the two. So you can still use this engine for a truck if you want to, but it's really going to be costing you a lot of money, especially going over those hills. It's ridiculous, okay? So this is the difference between the two cycles. Let me get into problem 2047 now. So that was a little bit of theory, if you wish. So we know that the efficiency for this cycle is 1 minus 1 over r to the power gamma minus 1, okay? That's it. That's basically for an Otto cycle. So it says in here, a VW Passat has a 6-cylinder Otto cycle engine with a compression rate, so it's a V6. And it has an R that is 10.6. That means, remember that ratio? That is 10.6 between VA and VB. Between this volume, let me draw the cylinder much easier, okay? So this is my cylinder. Between this is VA and this is VB. Or if you wish, this is VD and this is VC. This is VC, what I meant by it. And this whole thing now is VA. That ratio is 10.6, okay? Now, the diameter of each cylinder, called the bore of the engine, is 82.5. So this diameter, D, of each cylinder is 82.5 millimeter. That's because we can find the area now, where R is half of that D, okay? And then the distance that the piston moves during the compression, called the stroke of the engine, is 86.4 millimeter. So this distance, the distance, I'm not talking about the difference in volume. This distance is 86.4 millimeter. That's how much the piston has to go up and down, okay? So imagine yourself an engineer, and this is the specs that you have for that, that engine, okay? The initial pressure of the air-fuel mixture at point A is 8.5. So PA is 8.5 times 10 to the power 4 Pascal, which is just below the atmospheric pressure. Remember, it's 1.01, 10 to the 5. So it's about 20 Pascal less, which is meaningless for this order of magnitude of the pressure. So it's practically the atmospheric pressure, okay? This PA is Pascal, okay? So let's make sure that we're at it, okay? It doesn't mean that the pressure at point A. And the initial temperature is 300 Kelvin. So TA is 300 Kelvin. That's room temperature, okay? Which is the same as the outside air. Assume that 200 joule of heat is added to each cylinder in each cycle by the burning of gasoline. And that has, so added meaning QH. During this stage, that's what these added. So we added QH to 100 joules, okay? That's not the exhaust, that's the added. Of heat is added to each cylinder during each cycle by the burning gasoline on that has gas. So they tell you CV is 20.5, of course, joules per mole per Kelvin. really the mole is a number. And because you have to multiply it by the number of moles. And gamma is 1.4. Because it's mainly air, okay? A, calculate the total work done in one cycle in each cylinder of the engine and the heat released when the gas is cooled. Okay, we need to find W. That's the question. And then that's part A. And the heat released. So we need to find QC also. Okay. Here is a question. What do we know about this problem so far? Do we know its efficiency?
Yes.
Yeah, we
Yeah,
do.
because R is given. So 1 minus, because they gave us QH, they didn't give us W or QC to start working off of those. So we can't really do much with that. So it's 1 over 10.6. Is that 10.6 or is it 10 point?
I think it's 10.6.
Yeah, it is.
Yeah, it's 10. Okay, to the power gamma minus 1. And gamma minus 1 is 1.4 minus 1, which is 0.4. Okay, you will need a good calculator that can do this kind of calculations for you. To the power 0.4, okay? So since I have Mathematica open, so I'm gonna take advantage of it quickly. Oh man, can I kill this thing in here? I'm just doing the math in here, okay? Oops, I don't need that. Okay, so we have 1 minus 1 over 10.6 to the power 0.4. It's telling me 0.611064. Is that what you guys are finding?
Yeah, that's what I
Yeah.
got.
Okay.
Yeah.
So it's basically 61.1%. Okay. The reason why I'm retaining that one because it looks like they have 3 sig figs everywhere. These are known values, okay? Oh no. Let's assume it's 3 sig figs, okay? Anyway, if it's 61%, that's the efficiency of this engine. So now we can find what W is. W over QH is equal to 0.611. And we have QH, which is 200. So I can tell you what W is. W is going to be equal to 0.611 times 200. And that should be, I mean, I can do it by hand. By the way, the 2 zeros cancel. So I have 2 times 1, which is 2, and 2 times 1, which is 2, and 2 times 6, which is 12. So it's going to be 122.2, but I'm taking just 3 sig figs. So I'm going to say it's 122 joules. In my notations, in the notations we're adopting, this should really be negative 122 joules, okay? In the book's notations, so this is the book, it's going to be a positive. So that you can use in the book, delta U is equal to Q minus W. The way that we write it is delta U is equal to Q plus W, okay? So that's how much work is done. You guys understand the logic? Since we have R, we can find E. Since we have E, we have QH. Now we can find W. That's the reason why we went this route. The second part of this question was to find QC. Well, now we have multiple ways of finding QC. Either we use the formula that says basically that E is equal to 1 minus QC over QH. QH is positive, so we really don't care about it. Or we can say the same thing in here, that this is 0 or this is 0, and Q total, which is QH, okay, plus QW, QC is equal to negative W. If we use this convention here, if the book, you say it's plus W, okay? Well, QH is 200 plus QC, which we don't know, is according to us is equal to negative W, and W is a negative value. So according to us, it's going to be 122. According to the book, it's going to be 122 too, because the book puts the plus in here and W will come out positive. So it's the same thing, the same algebra. So QC will become 122 minus 200, and that is equal to okay. At some point in the day, you start getting basic algebra in here. 78, negative 78. Negative 78 joules. In both cases, it has to be negative, though. Whether the book or our convention must give us a negative value, because that's an energy lost. The same way I'm taking that rationale to argue that the work is lost in the energy is lost in the form of work. So that is a negative 122. Okay. Does this part of the problem sound reasonable to you guys? Part A. We found both W and Q.
Yeah.
Okay. Part B of this problem. Calculate the volume of air-fuel mixture at point A in the cycle. We need to find VA. Well, we have the pressure. We have the volume. Did they give us N? No. We have R, we have TA. TC, I'm sorry. The temperature at point A. We don't know what N is. We don't know what VA is either. Okay. What else do we know about this problem in here? We know the ratio of VA over VB. That is something we know. Do we know the entire volume, or we know just this volume? Let's mark it in blue. We know this volume, don't we? In blue. That is this area times the stroke. That gives us a difference between VA and minus VB. Put it in positive values. VA minus VB is D over 2 squared times pi times the stroke. Okay? And we know also that VA over VB is equal to R, which is 10.6. So we have two equations with two unknowns. So we're going to get two values. We're going to get VA and VB in the same time from these equations. Okay? That means that VA is equal to R VB, or if you wish, VB is equal to VA over R, and sub into this equation, and all of a sudden we have our value of VA. So we don't really need PV equal to an RT in this thing. So what we're saying is the following. VA minus VB is the stroke times the area. The stroke is given to us. And we know the ratio of VA over VB is equal to R. So that means that VB is equal to VA over R. So plugging into that expression gives me an equation for VA. VA times 1 minus 1 over R is equal to pi times D over 2 squared times the stroke. So that means that the VA is, we can compute it now. Does everybody follow the argument in here? So,
Yes.
Yeah. That's the area times the stroke, which is given, divided by 1 minus 1 over R. So we know the diameter is given to be 82.5. Divided by 2, but that's in millimeters, so it's 10 to the negative 3 squared times the stroke. The stroke is 86.4 millimeter, which is 10 to the negative 3 also, divided by 1, so this is VA, by the way, divided by 1 minus 1 over 10 to the power 6, I mean, over 10 minus 10.6, okay? I need you guys to get this number for us. Can you do that, guys?
Yes.
Yeah, but the answer is going to be in cubic meters. So it's a good idea to drop one of these powers and call the answer in liters, because that's a typical answer that you're going to get in there, okay? But it's still a very small number, and albeit this is no, it's going to be a small number, because you have 10 to the negative 3 to the power 6. It's a good, let's do this number, okay, because I'm kind of curious trying to see how big it is. Because this is a practical engine, by the way. This is not a hypothetical, you know, like a, so I have pi, okay, times, open parentheses, 82.5. Okay, I'm going to go straight to the power, 10 to the negative 3. Here I need to put the negative 3 in parentheses otherwise. Okay, divided by 2. The whole thing is squared. And times 86.4 divided by 1 minus 1 over 10.6. Close the parentheses. That's it. It's a half a liter. 0.51 liters. 0.10, because it's actually 599,972. So if I round it up, this is the actual number in liters. So it's going to be, what is it? 5.1 times 10 to the power negative 5 cubic meters. Okay, negative 5 or no, negative 4.
Yeah.
Okay, negative 4. Sorry about that. Okay, very good. Thank you, Isabel. Okay, yeah, so that is VA. Now we can go back to that expression that I started with and find N, because we probably need the number of moles at some point. They didn't ask us for it in this question, was it? Calculate the volume air fill mixture. So we found VA. So they didn't ask us for this number of moles, because we know PA, they gave us that it's almost an atmospheric pressure. We found VA. We know what R is. They told us TA is 300 Kelvin. So we know how many moles this takes, okay? So it's going to be a fraction of a mole. So that's part B. Part C. Calculate the volume of the air fuel, calculate the pressure, volume, and temperature of the gas at points B, C, and D in the cycle. Well, we know what VC is. First of all, we know what VD is. VD is VA, and that is 5.1010 to the negative 4 cubic meter. It's the same volume in DNA. And same thing, the volume in point C is related to, now, we need that volume in point B. And that volume in point B, or point C for that matter, is the same volume at point A divided by R, the compression rate, that's all. So it's this number divided by 10.6. So that's easy. So we can find what those volumes are. We can find what these pressures also are. What's the next part? Calculate. So we need to, we started with the volumes. We need to find the pressures. They're important. So the pressure in point A times the volume in point A to the power gamma is the same pressure in point B times the volume in point B to the power gamma. So that means the pressure in point B is the pressure in point A times the ratio of these two volumes, VA over VB to the power gamma. Well, we know this ratio is R. And we know this pressure is, they give us that value, which is 8.5 10 to the power 4 Pascal. So this is 8.4 10 to the power 4 Pascal times this ratio. And this ratio, VA over VB, is 10.6 to the power gamma, which is also known, 1.4. So we can find what that PB is using the adiabatic gas law, because that's an adiabatic process going from A to B. This is from A to B. So imagine we have found this calculation. This is an easy thing to do, okay? Once we found that, we can find what TA is. I mean, what TB is. TB, you can find it in one of two ways now. Either you use the ideal gas law, which you know that PB times VB equals to nRTB. That's to find TB, but we don't know what N is here. From that relationship, you can find what N is, remember? But if you don't want to do it, you can say PA times VA is equal to the same nRTA. Now, if you do the ratio of the two, you should be able to find what TB is. So divide these two expressions, the N and the N drops. You don't really need to calculate it. And you can find TB equals to TA times the ratio of PB/VB. Remember, PB, you just calculated it, which is related to PA, by the way, times this ratio, R to the power gamma, divided by PA, so that PA drops from PB, times VA. Well, VB over the power over VA, that's the same gamma ratio. So this is actually has to do with gamma, okay? As a matter of fact, this is to the power gamma, and this is 1. So this is actually some sort of a TA times something to the power gamma, 10.6 to the power 0.4 or something like that, okay? That is one way of doing it. The other way of doing it is, you know, QH, that is 200 joules, and that is equal to NCV times TB minus TA. I'm sorry, this is TC, not TA, TB. TC minus TB. You just found what TB is. Did we find what TB is? Oh, no. This is trying to find what TB. I'm sorry. So using this relationship, that's fine. So it's not this one. I thought we were in TC already. So in here, there is another method of finding TB, and that is using this relationship. TB, VB to the power gamma minus 1 is the same as TA times VA to the power gamma minus 1. And this gives you right away the ratio of TB as a function of TA, which is the same thing as that one, TA, except now you have VA over VB to the power gamma minus 1. And that is 10.6 to the power gamma minus 1, which is 0.4 times TA. So imagine you have done that. So in other words, this temperature is 300 times 10.6 to the power 0.4, okay? So in either way, you're gonna find TB, okay? Now comes the point C. We need to find for C. I mean the point C, not the, on C, we already found VC equals to VB, which is VA over R. So we know what the volume is. Now it's a matter of finding what the pressure is and what the temperature is. Probably the easiest way in this case is to find what the temperature is. For that, we know that QH is equal to NCV times this TC minus TB. You see, I was jumping the gun in there earlier. So we know what TB is. It's here. We know what CV is. It's 20.5. We know what QH is. It's 200 joules. We can find what N is using any of the relationships you wish. You can go back to this expression if you want to, or the very first one that we started with. Since we know what PA is, what VA is, what R is, what TA is, VA, we computed it. It's this number in here, 0.5 or 5.1 10 to the negative 4. So we have the volume, we have the pressure, we have R, we have TA, so we can find the number of moles. So we really need that number of moles now. It's not an option. And then we can plug it into this expression and find TC equals to TB plus QH over that number of moles times CV. And that number of moles is PA VA over RTA from the previous expression. So theoretically, this is computable. TC, remember TB is calculated in here. QH is 200 joules. PA is 8.5 10 to the negative 4 atmospheric pressure. VA we found is 5.1 10 to the negative 4. So the 10 to the positive 4 and 10 to the negative 4 cancel in this expression, divided by R 8.314, and TA is 300 Kelvin, and CV is 20.5. Does everybody agree that this is calculable? With everything in here and in here?
Yes.
You're wondering where TB is coming from? Here it is. 300 times 10.6 to the power 0.4. So we can find TC. Once we find TC, we go back to PC, VC equal to nRTC. So we just found TC. We know what R is. We just found what N is. And we know what VC, which is VB, which is VA over R. All we have to do is use this expression to find what the pressure at that point is. The last point in here is the point D. Well, for D, we know that VD is equal to VA. Okay? So we know the volume. We know that the process going from C to D is an adiabatic process, meaning that PC, VC to the power gamma is equal to PD times VD to the power gamma. From here, we can find what this pressure is, which is just PC times VC over VD to the power gamma. Well, we know what VC over VD is. As a matter of fact, we know that VD over VC is R. So this is going to be PC, the pressure upon C, times 1 over R to the power gamma. Gamma, not gamma minus 1. Okay. The reason why this is computable, this is 10.6 to the power 1.4, and this is PC that we just found from this expression. So we can find what PD is, what that pressure is. Now, having said that, we can use the same relationship for the temperature. Remember, TD to the power gamma, not TD, there is no power gamma, I'm sorry, TD times VD to the power gamma minus 1 is TC times VC to the power gamma minus 1. Again, we need TD now. That TD should be equal to TC times this ratio of the volumes, which is VC over VD to the power gamma minus 1. Again, VC over VD, that is actually VC over VD, that is 1 over R to the power gamma minus 1. And TC, we're assuming that we did this calculation in here for TC, which is this one. So we have TC. So we can find what TD is. So we have TD, which is computable from here. We have VD, which is VA, and we just found what PD is. We can check, if you like, or do whatever you want to, that the other relationship will give us the same thing. PD is equal to nRTD divided by VD. Because we just found TD, we have found N a long time ago. We have VD, which is equal to VA, and PD, we just calculated it earlier using the adiabatic process. So we can, so there is all kinds of ways now to do these calculations. Does everybody agree that this is calculable all the way through?
Yes.
Okay. Anybody else to make sure that in case I have more than one on board?
Yes.
Yeah.
Very good. So this is all the numbers. Just plug in the things and just follow the logic in here. D, compare the efficiency of this engine to that of a Carnot cycle. This is where you really need to do the calculation. So E Carnot must be 1 minus TC over TH. And TC is TA actually. And TH must be that at point C, TC. TA is 300 Kelvin, and TC is all of this stuff in here, which is TB plus QH over PA and all of that. So you do this calculation and you put it in here. And this is the point of the discussion today. Check that E of Carnot is greater than, at worst, is equal to E naught. Remember, E naught is 0.611, 61%. This better be more than 61%. This closes the points of the discussion. Remember, was to put the second law in your own words, using the first, the second, and the third formulation. Now using the probability W as maximum, and now to check that this engine from this example has indeed a lower efficiency. 61% must be less than that of Carnot.
Wait, can you repeat the law thingy again real quickly?
Okay, can I repeat what the discussion points, or how to find EC?
The discussion one about the law.
Okay, so you're supposed to state the second law using, remember the fact that Mr. Carnot has said that heat cannot continuously go from TC to T hot, from a cold source to hot source. That's the first one we started with. The second one, we stated that the entropy can never be negative. This is a no-no, okay? The first one, heat going from TC to T hot, is a no-no. Those two statements turned out to be equivalent, and I made the argument for them using Clausius arguments. And then we found now that W is always increasing, always maximum. That's all of it is the same thing. It's the same law. Second law, you formulate in terms of probability, or in terms of entropy, or in terms of the first formulation using the fact that heat cannot continuously go from the cold source to hot source. Okay, so this is basically what I want you to put it in your own words. And then check this engine, which is from problem 2047, to make sure that this problem gives me an efficiency. If it were Carnot, which is TA over TC, if it were Carnot, it's going to be higher than, at worst, equal to this 61%. So the efficiency of the Carnot can be 62%, 63%, I don't care. 99%, I don't care, as long as you find it more than 61%, 61.1%. That's what we found for this VW Passat. We want to make sure, had it operated using Carnot cycle, that its efficiency should be higher. So you do the calculation in here. You have TA, you have TC. I mean, you can calculate. TA is 300 Kelvin, so this is a given. So all you have to do is make sure you find TC from this calculation, and you do 1 minus that ratio of 300 over that number, and this should give you a number that is more than 0.611. If it does not, I need to know about it. We need to know about it, because this violates all of this formulation of the second law. Because that's another way of putting it also, the second law, that no engine can have an efficiency more than EC. This is also no-no. Okay, this one also can be stated in W can never be the same or less, always higher and higher when systems interact thermodynamically. Okay, this is what the thermodynamics say. You can never remember tomorrow, but you can always remember yesterday. That's actually another way of saying it too. Okay, do we understand this problem?
Yes.
Yes.
Okay, I know it's
So for the discussion, you only want part D, correct?
yeah, I want this thing in here, which is a big deal. It's not just an only, it's the whole D. Okay. Did I make a big emphasis on it, Maddie?
Yes.
Okay, I'm making a big fuss over it. I know that. Okay. Okay, let me take another example. Hopefully, it's a lot lighter than this one, which, as I promised, and there will be more examples. And then jump into the lab and see how we do. Okay. And that is problem 2022, because it has to do with the entropy. And I think if we have time, we'll probably have to do another one. Okay, hold on. So this one here, you decide to take a nice hot bath, but discover that your thoughtless brother or roommate has used up most of the hot water. Okay. You know, you look at the, turn on the hot, it's all gone. Okay. So what you do, you decide to fill the tub with 195 kilograms of water, okay, at 30 degrees Celsius. So this is T1, okay? And attempt to warm it by pouring 5 kilograms. You take a bucket, basically a gallon, slightly more than a gallon. That's what the 5 kilogram of water is. And you fill it and you warm it. Look at the words in it, boiling water. So this is M1. M2 now is 5 kilograms of the same stuff, basically, except now its temperature is boiling, which means that it's 100 degrees Celsius. That's when it boils, okay? Is this a reversible or irreversible process? Obviously, this is an irreversible process. You cannot take the 5 kilograms of water and basically all of a sudden separate it. It's not possible. So this is an intuitively, and we'll see it through the entropy, okay? So this is an irreversible process. So that should be easy, okay? Part B, calculate the temperature of the bath after. So when you mix them, remember you do a calorimetry in this case, the heat lost from the hot source, which is this one from this hot source, is gained by the cold source. The temperature of the cold source go from T1 to T of equilibrium. This temperature go from T2 to T of equilibrium, so that the heat that you lose is from the hot source, QH, is equal to M2 times C, it's the same C, by the way, times delta T. And delta T in this case is T final, which is T of equilibrium. I'm sorry, T initial, which is higher. Okay, so I'm going to call it T2, just taking the absolute value now, minus T of equilibrium. This must be equal to the heat that was gained by the other one, namely QC, to warm it up. And that was M1 times C times the final temperature, which is higher than the initial temperature. So this warms up and takes its temperature from T1 to T equilibrium. I'm using this QC and QH. This is not an engine. I should have really called them Q2 and Q1. Okay, so that we don't get confused with the engine. There is no engine in here. Just basically, you have two mixtures that you mix them together. This is calorimetry now. Remember that calculation I mentioned earlier for the calorimetry? So now we want to find T equilibrium that makes this equation possible. This equation possible means that M2C times T2 minus T1, T equilibrium, times, must be equal to M1C times T equilibrium minus T1. Cancel the C from both sides and do some algebra. I'm going to have M2 moving to the other side. With a negative sign, it's going to be a positive. This negative moves to the other side, also becomes a positive. So what I'm going to end up with is M2 T2 plus M1 T1 divided by M1 plus M2 is equal to the T equilibrium. This is the equation of the center of gravity, if you remember it, the center of mass. If you sub this value for x2 and this value for x1. Do you guys remember this expression when you did in physics 1?
Yes.
Okay, So that's exactly the same thing, except now instead of, that's what the temperature is going to be. It's going to be weighted by this masses because it's the same substance now. Had it been different substance with different specific heats, then we would worry about this C in here, okay? So T equilibrium is going to be M2. Now I have to be careful with this things in here, which is M2 times T2, and T2 is, what is that value? It's
100?
100.
plus, because I'm using the difference in here, the difference doesn't matter as far as converting to Kelvin or not, plus M1, M1, M2, let's put the values in here. What am I talking about? M2 has a given value, it's 5 kilograms. No. So this is 5 kilogram times 100 plus, doesn't matter, times 0. No, not 0, it's 30. So we need 195 times 30 divided by 5 plus 195, which makes it around 200 in the denominator nicely. So the T equilibrium should be equal to 200 in the denominator, 500 plus 30 times 90, 195. Cancel this, cancel that, cancel this, 0. Cancel this, gives me 4 in here. This divides by 5. This gives me 10. 195 divided by 5 is what? 41? Is it?
Wait, 195 divided by 5?
No, it's not. It's 39. 39.
Yeah.
Is it 39?
Yes.
Yeah. Okay, you can find the number in here, please. Okay. Can you find the T equilibrium in this case?
I got 31.75.
How much?
31.75.
Yeah, same here.
Same.
Wow. It did not warm that much, did it? Because he's got only a 5 kilogram versus 195 kilogram. Obviously, it's not going to shift anywhere in the middle. Okay. So 31.5 degrees Celsius. And calculate the net entropy change. That is the key question in here, okay? So let's find delta S for the entire system. Delta S for the entire system is equal to MC M2C ln of T final for the first one. Remember, it was 100, it dropped to 31.5. So it's going to be, the final one is 31.5 plus 273 divided by 373, okay? Plus M1C times ln of 30 plus 273 divided by 273. So let me do this calculation quickly. How much is the specific heat for the water? It's 4,190 joules per kilogram. Okay, so that we have the number correct in here. Okay, so let me try to do it quickly in here. Or let's start a new page. Or
I think it's 31.75, not 31.5.
Yeah.
okay. Why am I doing that? 7.5. So let's do it in here in the calculator quickly. So I have M2, which is 5 times I'm going to take the C out as a common factor. So it's 4,190, open parentheses. The first one is M2, which is 5 times ln. In mathematics, it's called log, okay? In the base of 10, you have to use log 10. So open parentheses of 31, open another parentheses, 31.75 plus 273 divided by 373 plus 195 times log of open parentheses of 30 plus 270, that's 303. 303 divided by, why is it divided by? No, it's the same 31 points. I'm sorry. Here, it should be 30 plus, so the denominator is 30 plus, that's the initial value, and the final value is 31.75. Okay, it's the final over initial. This was at 30 degrees Celsius, and now it reached 31.75. Okay, so I have to be careful in here. So the numerator is the same thing as the first one, which is 31.75 plus 273. Now close the parentheses, divided by 303. Okay, now close this. Oh, the log function doesn't take parentheses, so I have to fix my logs. Let me find also this log in here, which take this argument, otherwise Mathematica will not like it. I hope you guys are doing the calculations and not relying on my numbers in here. Okay, it's telling me the net difference between them is 471 joules. What are the units now? So this is kilogram, and this is a joules per kilogram per mole. So joules per kilogram per Kelvin. Okay, so the kilogram cancels the kilogram, so it's going to be a joule per Kelvin at the end of the day. Okay. Did you guys got the same number, or did I make a mistake in here somewhere?
Can you repeat your number?
471.6.
That's what I got as well.
Kelvin.
Same.
Okay, here's the big deal why this number is good, okay? I don't know if it's correct or not, honestly, so I'll have to probably double check myself. But the reason why it's not wrong is because it's positive. And that is because we said the process is reversible. So the entropy cannot be zero, as a matter of fact. If it was reversible, we could end up with zero. The worst case scenario in here, we end up with delta S being negative. If we ended up with delta S being negative, we have a problem. We cannot go home then. We have to stay here until we fix it. So this is good. It doesn't mean it's right, but at least it's not wrong. Sounds good?
Yep, sounds good.
Okay, so I think we did the two problems that are interesting. Do you want to do another problem, or we jump to the lab? You guys up to it? Okay, it's really up to you. I'm in either way.
I don't want one. I don't want another one.
Anybody else?
I mean, yeah, let's jump to the lab.
Yeah.
Getting tired of problems, huh? Okay, so let's jump in the lab. Let me go and find it first. It's this browser. And let's go back. I wish we were on campus though, so that we can meet and go to that nice STEM room. I don't know if they're still, they will have it open or not. I know we can do it now because they have a special arrangement, even nowadays. And that's where we hang around in there. So what is the lab? You guys know what I'm talking about in the STEM center? Yes, no?
I don't.
Yeah, no.
Okay. In the STEM center, I don't know if they closed it or not, but it's been since before Corona, we used to hang around in there, and a lot of my students and myself we hang around, do all kinds of things, problems in there. Yeah, it's been 2 years, you're right, okay? But now since the campus is back, so hopefully they will open it again. Okay, so let me share with you the screen. Let me first of all separate it from everything else. And let me share with you the screen for the lab so that we have the same things in here. Share. Okay, the lab has the instructions in here, which you're going to open by itself. And there's a bunch of sheets in here, 8 of them. Each and every one of them has 2 engines. Oh, no. Each and every one of them has an engine. So you have a total of 8 engines. You are required to do 2 of them. Please do not do 1 and 2 everybody, okay? I want to really see variety in here, and actually for your own benefit, do all of them. Do all of these engines, okay? And again, you have the rubric in here, and this is when it's due. Okay, we'll probably have to change this due date in here. And I will think about this, okay? I may have to make it a little before the exam. So we'll see. Okay, so most likely it's going to be due the 22nd, which is 2 days before the exam, because of how important this one is for the exam. So let me download the instructions. Come on. Let me save it first because, yeah, can I do it this way? And let me move it. And let me go and stop sharing that screen and share the instructions before we got into this specific sheets in here. Share. As you can see, your name in here, it's all about the heat engines. And this is the hot source, the cold source, TC and T hot. And this is some of the examples. Okay, here is conversion factors, okay? When you measure something, of course, they give you the probably the pressure, atmospheric pressure. You can convert it to Pascal by multiplying it by this number. And you can convert it in joules per cubic meter versus Pascal and converting it into centimeters, which is the 100 divided by 1 centimeter. So at the end of the day, the units in here for the pressure are going to be in joules per cubic centimeter. Okay, just come back to this expression, and you will find this conversion terms. The temperature is going to be, for most of these engines, TC and T hot are given by 300 and 400 Kelvin. Okay, room temperature around boiling temperature of water. Now, Vmax in this example is 1,000 cubic centimeters. So this is all of the units in terms of the units. This is what we discussed it earlier. Qin, which is Q hot, Q out, which is QC, the entropy, the temperature, which is the highest temperature of the process, TC, which is the lowest temperature in the process. Had it operated as a Carnot engine, it's going to have 1 minus TC over TH, okay? You have the maximum pressure, the minimum volume, the maximum volume, and that is going to be the compression rate, so on and so forth. So this is basically what the PV diagram is interpreted. The W net in here, we're following in the lab the same thing as the book, but hopefully you understand that the positive value in here you end up with really means that it's work done by the system, meaning it's energy lost to the environment, okay? And this is the expression. You can take it in absolute value, if like, from the expressions that we've been working with, or if you follow systematically this argument, this is what we did it. QH minus QC, QC turned out to be in absolute value negative. So we're taking all of this expression is an absolute value. Delta U is always NCV delta T, and you have PV equal to nRT, which is the ideal gas law. This expression follows the book. Okay, the biggest mistake in this lab in here is this deltas. And I always intend to fix that, but I really don't get around doing it. It doesn't mean a thing to say delta Q and delta U. There is no such a thing. There is a Q and there is W. Because there is no initial work and final work, and the difference between them is delta W. They are not state variables. You're not allowed to use the deltas. I mean, for specific calculations, you may use it, but representing that integral only. But what you really mean with it is that this is a path-dependent value. So you cannot really put it in general in this law. So it has to be Q minus W. And that's how Clausius wrote it initially. He wrote it without this because he really knew what he's talking about. He was talking about. So please fix that, okay? Although in some of the calculations, you might end up really doing this integral that way. Same thing with a delta Q. You might end up doing this integral, but that's a mathematical thing only. It doesn't mean that it's a physics thing. The physics requires that this be a Q and this be a W. And in the integration, that is when you end up with the upper limit minus the initial limit. That's all, okay? this is how we explain the engine. This is W net, this is the QC, this is the Q hat. The difference between them is W net. And that is basically what we did so far. The efficiency in this lab uses the letter epsilon because it's typically used for the efficiency also, not E, the way we used it. The isothermal process, we found W to be equal to nRT ln of final over volume final over volume initial. In the case of the isothermal, these two values will be equal, following the convention of the book. In our convention, there is a negative sign floating between them, okay? And this is your isothermal process. This is the isochoric process. In this case, delta U is equal, here, delta U is equal to 0 because temperature doesn't change. In this case, the temperature changes, so it's NCV delta T. It's always NCV delta T, by the way, regardless of what the process is. Except in here, delta T is equal to 0, that's all. Because it's an isothermal process. T is constant, so delta T is 0. So that's delta U. Q, not delta Q, is it turned out to be nRT ln of the final over the initial. And the same thing for W, because we're using in this convention, in this lab, the convention that delta U is Q minus delta U, minus U, I'm sorry, minus W. Delta U is Q minus W. So since delta U is 0, these two quantities must be equal in absolute value, okay? And delta S is just Q over T because T is fixed. So it turns out to be NR of the log of the final over initial. Okay, here in the isochoric process, this is a summary of everything we did actually. It's NCV delta T. W is 0 now because it's an isochoric process. The volume doesn't change. And since the volume doesn't change, so delta U is the same as Q. Both of them are NCV delta T. And in this case, I have to integrate this expression from the initial temperature to the final temperature. And that is what gives me log of TH over TC. And we did this today. We calculated the entropy for an isochoric process. For an isobaric process, also it has the log, except that the coefficient has a CP instead of a CV. And for the calorimetric process, also it has an MC times the log of the final temperature over the initial temperature, by the way. It's not listed in here because it's not in the PV diagram, that one at all. Okay, it's not part of the engine processes. So NCV delta T, NCP delta T, and in here, the pressure is constant. So the work is P times the difference in volumes, that's all. Or NR10 delta T because CP minus CV is always R. Okay, it's the same thing. Now in an adiabatic process, Q is 0. That's by definition of an adiabatic process. So NCV, which is the delta U, is the same as W, except there is a minus sign. So here, the minus sign is actually needed for some reason, okay? Not just because somebody, it's always true in this case, because if we take the convention of the book, we have a minus something positive. If we take our convention, we're adding something negative, so we're gonna end up with the same expression in either case, okay? Because Q is there. So this is a summary of everything that we learned. This is actually the entire review for the exam, with the exception of calorimetry in here, and some of that thing that has to do with the mean value and things like that. So again, isovolumetric, isoprocess. Now the different values of gamma for a monoatomic gas, 5/3, diatomic gas, 7/5. Roughly it's 9/7 for a polyatomic gas, and that is CP over CV. CV is 3/2 Rs, which put it around 12 something joules per Kelvin per mole. And 5/2 in here puts it around 20, and this one will put it more than 28 or something like that for CV. CP, add 1 to any of these values. I mean, add the R to any of these values. So 3/2 becomes 5/2, 5/2 becomes 7/2, and 9/2 becomes, 7/2 becomes 9/2, and so on and so forth, okay? If you know gamma, this is how you find CP. It's gamma R over gamma minus 1. If you know gamma, this is how you find CV, which is R over gamma minus 1. And this is what gamma is. So all of this is summary of everything we did. So this lab is important for your review. And it's not just because of this, there are more stuff coming to it too. So the isobaric process, this is a repetition. This is a relationship that we found. That's what I was talking about. Cp is Cv plus R. The adiabatic process, again, we calculated, we did this in lecture, and this is another derivation for it. PV to the power gamma is constant, and TV to the power gamma minus 1 is constant. That was actually the previous lab too. Okay. Given gamma, use equation 6 to show that, okay, this is algebra, okay? If you know gamma, which is Cp over Cv, use this relationship, which is Cp equal to Cv plus R. Divide this expression by Cv. You will find gamma on one side. You will end up with 1 plus R over Cv. Solve for Cv, you will get Cv, okay, as equal to this expression. Now, since you know what Cv is, you just solve for it in terms of gamma. And gamma is Cp over Cv. Cp is equal to gamma times Cv. So all you have to do is just show that this is the same. So this is straightforward algebra for question 1. And now here, the Carnot cycle, we did that last time. This is the Carnot cycle. You have an isothermal, an adiabatic, an adiabatic, isentropic, in other words. Okay, the entropy doesn't change. Okay. And we did the calculation. We found what the efficiency of the engine is. We have TC, we have TH. And we did everything for this engine except at constant TC, the first part, here is TC, constant TC, in this compression stage. So when I say in here, this is the process, you have 4 processes: constant TC, constant S min, the entropy is minimal, constant TH, and constant S max. So this is an isothermal at TC. Delta U is 0 because it's an isothermal. Q should be just negative this value, an RTC, and negative is leaving the system, that's all. W, it has a negative in this convention because they have to subtract it in order to add it to the energy. In our convention, we leave it positive, so it's going to be, in this case, positive because you're compressing the gas and you're adding energy in the form of work, that's all. So in either convention, this is Vmax, this is Va. And does this check? Of course it does. Because if you take this number, you subtract from this one, you're going to find 0. S min, in this stage, Q is 0. There is no heat. So in this case, delta U is the same as negative the W in this case, the way that they wrote it, or numerically, that's exactly the same value. So we would have gotten the same answer if we follow the other convention. Both of them will give you 3. Now, does it check that delta U is equal to 0 plus this number? Of course. NCV delta T is equal to 0 minus this number, so it's going to be NCV delta T. Yes, it checks. TH, that's this stage now, this expansion. Of course, it's the opposite of this one, except happening at TH. The last one in here, S max, is the opposite of S min, except it's happening at a different level in here. In this case, everything checks. And the U net in here, which is the sum of all of this energy, should be 0 because it's a cycle. So if you add all of these numbers, you're going to get 0. And if you add all of these values, it should be W net. Okay. The network is this value plus this value plus this value plus this value. Of course, these two, they cancel. So in this case, you end up with, this is the W net. Okay. This is the sums, of course, of all of this. This is the cycle, if you wish. Okay, the Qn, how much heat got in? Well, this is how much heat got in, the hot source. How much heat was lost? It's this one. So this is the hot source, that's the Qn, that's the Q out, the other one. Is W net equal to Q net minus Q out? Obviously, because delta U is 0, so we better check that this one, Qn, which is this value minus this value, does it check to be equal to that one? And the answer is yes. If you subtract this number, subtract this number from this number, that is exactly what W net is. That is for the entire process, U net is 0, and here it is. Okay. The efficiency in this case turned out to be just W net over Qn, which is Q hot, the way we defined it. And if you do the algebra, everything will cancel because this is the W net, by the way. nRT and the logs will cancel, divided by TH, where the nRT and the logs will cancel this stuff in here. And we made the case where the logs cancel. Okay. So we are done in here. That's actually the case where the logs cancel in here. That's why the epsilon, that's why the logs cancel in here. Given the data in table 1, if Vmin is 200 cubic centimeters, so they gave you Vmin, use equation 8 to solve for the values of the points listed in equation 7. So they gave us Vmin. Remember, they gave us Vmax to begin with. They gave us TC and TH. Okay, so we have a lot of these values. So we're supposed to use this points in here, since they gave us these points, and we can find solutions for all of them. Now, I trust that you guys should be able to follow this calculation and find all of the numbers, because remember, Vmax is given to us, it's 1,000 cubic centimeters, and TH is given to us to be 400 Kelvin and TC to be 300 Kelvin. So we have a lot of these numbers in here. Okay. Sounds good, everybody?
Sounds good.
Okay. So this is the Otto engine that we did today. Okay. Nicholas August Otto. Okay. Sounds like it's the reason why they call it automobile is because of his name, but it's not. Okay. So again, this is the calculation we did today, and TATB. So the efficiency turned out to be 1. Okay, we use the symbol rho instead of R because the book uses R, and actually the common symbol again uses rho for the compression rates in here. Okay. It was 1 over R to the power gamma minus 1, which you can write it because, you know, when you take it to the numerator, you just change the sign. It becomes 1 minus gamma. Okay, so the same thing. So you can follow the logic in there. Now we know to take advantage of the equation 10, so to find these relationships between them, and compression rate is given by that. This produces. Show that T alpha. So again, this is just the thing we did in lecture. TA, not T alpha, is equal to TC. Oh, T alpha and T beta. Let's look at this convention here. So this is TC, T cold, that is. This is T hot, and those are the two intermediate temperatures. Okay. The min, which is PA, and V max, which is this volume, the ratio of it is rho. Okay. So we are supposed to use a relationship in here, the adiabatic process and this adiabatic process, to find these expressions. And we did them actually in lecture. If you go back today to lecture, you will find these relationships in here. Okay. So T alpha and T beta are related to T gamma. So in other words, this is what you got to do for one of them. T alpha times V max to the power gamma minus 1 is equal to TH times V min to the power gamma minus 1. And divide by V min, and you end up with V max over V min, which is rho. So that's how you find one of these two relationships, which is this one. The second one, T alpha and TC, it's identical, except for the other adiabatic compression, that's all. Okay. The Otto engine is an internal combustion engine that burns gasoline inside of its cylinder. What value of gamma should be used for this engine? Obviously, it has to be 1.2, 1.4, okay? And V min equals to 200 cubic centimeter, which is the efficiency of an Otto engine. So we have V min, which is 200 cubic centimeters. We have V max, which is 1,000. Obviously, the rho in this case, or the R in this case, is 5. So all you have to do is find the efficiency using the formula, which is 1 minus 1 over 5 to the power 0.4. Okay. Ignore this part in here. So we're not in the lab to do these two questions. Questions 5 and 6, skip them. And this is now what the process is. So you're supposed to get 2 or 3 worksheets, okay? Each worksheet represents a fictitious engine having 3 thermodynamic processes. Write the equations, write out the equations at the endpoints. And if one of these processes is adiabatic, apply the adiabatic law. And using the equations, basically. So let me explain this one by doing it practically. I'm going to take a random engine from this one, and I'm going to do the entropy later on by calculating it for this different processes and do the conclusion. So let me get into this back into the slab in here. I don't know what screen is showing in here. So I'm going to pick up engine. I have 1, 2, 3, 4, 5, 6, 7, 8, 7, 8. Which one do you think we should pick at random? Give me a number. Don't tell me 1 and don't tell me 8.
5.
That sounds a good number. Thank you very much. Have a nice day. So I'm going to pick up 5. Okay. 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 So I'm going to share with you this engine. Obviously, all of these engines are 3-stroke engines, which means that they're not practical. Okay. So the first part in here is to write the equations. I have in here 3 processes in engine 5. The first one, I always start from here, from Vmax to Vmid. Okay. In this case, it's an isobaric process. And also from Vmid to Vmin, that's actually an isentropic process or an adiabatic process. And from Pmax to Vmax, I mean Vmin to Vmax, the last one is actually an isothermal process. Okay, the first thing we need to do is write the equation, the PV equal to nRT for all of these parts. So we know Pmax times, no. I'm starting with that point. So it's Pmin. Look at the pressure in here. It's a Pmin pressure at that point. So it's Pmin times Vmax is equal to nR Tmax. I don't know what that temperature is. That's equation 1. Equation 2, at point mid, we know the pressure there is P min times V mid equals to nR Tc. Tc. Okay. This T is actually TH. The reason why it's TH is that's a thin isothermal. Does everybody agree in that point it's TH? Yes?
Yes.
Yes.
Okay. Okay, the last point I need to write this equation for is the point at the top, this point in here. And that has Pmax Vmin is equal to nRTH also. So we have 3 equations, the state equations. Now, we know also that Vmid, no, let's write it in terms of temperatures is better. Tc times Vmid to the power, I don't have gamma, so I'm going to write y, okay? -1. So I'm going to go up in here. Let me make a note to myself. Gamma is 1. The reason why is why. If I don't do that, I probably will forget, okay? So it's better that I take that. And if I don't, I write it gamma, it's going to take a long space in here. So the equation becomes too ridiculous in here, too big. So it's equal to TH times Vmin to the power, open parentheses, y minus 1. Did I miss another equation in here? Am I missing another one? The isothermal, it's fine. I mean, we can actually go, I mean, crazy about this one in here, okay? For the process, actually, I can write it in here. For the process, going from 1 to 2, I always, 1 is always to the bottom, okay? And then I follow the arrow. So from this process, it's an isothermal process. So I know W there, W in that process 1, 2 is equal to, in our convention, but we're going to stick with the book right now. So it's going to be, because it's going to be a negative value, for us, it's going to be a positive, by the way. It's going to be in CP, because this is an isobaric process, times the final temperature, which is TC, minus, or yes, TC minus TH. It's going to be positive according to the convention of the book, so we better put a minus in here, okay? Or if you wish, an absolute value in here, just to save ourselves a headache for right now, okay? Now, that's one thing. Do we know what Q is? Absolutely. So Q from 1 to, this is going to be clearly negative because we're compressing it, so it's dumping heat in this case in here. And there is no heat in the second stage, but there is heat also gained through the last stage. So this is going to be a negative value, and it's going to be equal to, oh, why did I put this one? I'm sorry, so this is wrong. This is just the pressure times the volumes. I'm thinking in terms of the temperature, okay? I'm thinking in terms of heat, so this is wrong, okay? So it's going to be Pmin times Vmax minus Vmin. You see, if you're not careful. Now this is the one that is in Cp times Th minus Tc, and this is better be negative, okay? You can find delta U if you like and do all of the other things for it. For right now, I'm gonna stick to this value. From T to 3, that is the Q equal to 0 stage. And also the W in this case is equal to, we're gonna take it in absolute value in this case, okay? It's gonna be in CV times delta T. Why? Because Q is 0, so delta U is, delta U is equal to W in this case. So it's T hot minus Tc, because delta U is W. In the book, it's going to be minus W, so if we're going to follow the convention of the book, we better write it that way. Okay, so I'm taking it in absolute. The last stage in here, which is 3 to 1, back to a starting point, is going to give me, this is an isothermal, so delta U is equal to 0. And in this case, W from 3 to 1 is equal to QH, Q hot, okay? And this is going to be NRTH ln of open parentheses, which is V max over V min. Okay, so these are some of the formulas, and I may come back and supplement more formulas that I know. So in this place in here, all I'm doing is writing the equations I know. Okay, some of the equations have to do with PV equal to nRT, others have to do with the process itself. Okay, so let's come in here. This is given, Vmax is given, TH is given, Pmin is given, gamma is given, and TC is given. All of this are given. So we need to find Pmax. Is there an equation in here? V min is not given, so I can't use this equation in here to find. So Pmin is given. Here is Pmin. times V mid is not given, so we need to find it, equal to NRTC, and TC is given. So TC is given, P min is given, and N and R are given. No, N is not given, I'm sorry, N is not given. So we're supposed to solve these equations and find what we need to find, namely V mid, okay? N is not given, TC is given, TH is given, P mid, P min is given, okay? But if I take the ratio of these two expressions, V mid over V max is TC over TH, because this pressure cancels that pressure, N cancels that N, and R cancels that R, and that gives me in here V mid equals to TC over TH times V max. So it's going to be equal to V max times, open parentheses, TC over TH. Does everybody see how I was able to solve? What is this one? Yeah, it's already in here. So V mid is equal to V max times TC over TH using the first equation and the second equation. Yes, no, maybe. How you
Can we-
solve for V?
Can we take a look at the equation again, just to be sure?
Here is what I found. V mid equals to V max times the ratio of the two temperatures. All you have to do is take the ratio of these two expressions.
Okay, I see it now, yeah.
Okay. So this is, we don't know, so we found it. We need to find P max, okay? Because that's not known also. P max is not given. So P max times V min is given. But we don't know what NRT N is. So we can't use that expression to find it, okay? Let's see what else we can do in here. We just found V mid in terms of V max using this equation. Now we should be able to use, why is this? Yeah, V min and V mid. We could have used this one actually to find also V mid in terms of V min. Now we need to find this pressure, okay? Okay, times in here, I forgot the times, okay? So we need to find P max. Okay. We have V min, we have V max. If we take this equation and divide it by this equation, the volume V min over V max, those are two given. V min, no, we didn't, I'm sorry. What am I saying? V min is not given. So we need a way of finding this pressure. Okay, there is another relationship that is useful for us in here, and that is P max times V in that point, which is V min, to the power gamma equals to this pressure, which is P min, times V mid to the power gamma. Okay, this is also because it's an adiabatic process. Okay. It may be useful now to find what N is. It may be useful to find this number of moles is, because I can go back to this expression here. I have P min times V max, and P min is given, and V max is given, equals to NRTH, and TH is given. So I need to find the number of moles in here from this equation in here, from the first one. So the number of moles is clearly P min times V max divided by RTH. So this is actually a useful thing in here to have, which is P min V max, P min times V max divided by RTH. So now we have this expression. Now we can take this to find Vmin. Am I missing another equation or am I overthinking it in here? Vmin equal to nRTH. Yeah, P max Vmin is equal to P min V max. Okay, this equation in here, the third one and the first one. We have V max, we have P min. We don't have P max, we have V min, and both of them are equal to nRTH. So in this case, it's going to give me straight P max equals to P min times V max over V min. But I don't know what V min is. Sorry, I'm sorry. And we have this equation in here that also has P max in it and V min in it. Okay. So we have two equations that we really have to solve them. We have equation in here, this one. That involves two unknowns, P max and V min. TH is known. And we have this equation in here that involves P max and V min also. P min is given, here it is. And V mid, we just found it. So we have two equations with two unknowns. We need to solve them to find what P max and V min is. Does everybody understand the algebra now? That these two can be found from these two equations?
Yes.
Okay. So we have to fill the gap in here and find them. Then we're going to find the ratio of V max over V min. V max over V min. Once you find them, once you find what V min is, just take this value, which is given. It's going to be in terms of V max, by the way, and the ratio is going to be rho. Okay, this is given. You don't need to have to fill it out in any way, okay? Because these two things are given. So this is, you don't have to fill out anything. No need. Okay, so just leave it as is, okay, for this value. Now the last one in here, since you found n, all you have to do is just multiply this one by Avogadro's number, Na times P min times V max divided by RTH. Okay, so the missing thing in here is to solve those two algebraic equations that I pointed X on them. Once you do find that, you find the rho is. Okay.
Can you scroll back up real quickly?
Here.
Okay,
So you
thank you.
have to. Yeah, once you find those, you're going to find what V min is, what P max is. From here, once you find V min, you take that ratio and find what rho is. Now comes in the good part, where you're given TC is actually 300, TH is 400. V max is equal to 1000, and P min, they tell you in the instructions how much it is, and gamma is 1.4. Now you're going to do the algebra. You're going to do the numbers. You're going to, instead of writing here, you write formulas, and here you put in values. Does everybody understand what we're doing now? Yes?
Yes.
Okay, very good. Now here is a task again repeated, but this time for the energies. Those are the state values. Now I want to find the delta U for the P min for this cycle. For this one, well, the delta U should be always NCV delta T. Okay, N times CV, and N I just found it. It's this number times CV. And CV you can express in terms of gamma. Remember that relationship that you have up there, which is gamma times R. I mean R divided by gamma minus 1. That is your CV. So you have N, you have CV. N is from here, and CV from the relationship that relates gamma, because gamma is given. You don't have CV in here, so you better find it, okay? Remember from previous questions that you're supposed to find it. And then you multiply it by delta T, and delta T is just TC minus TH in this case. This is TC, this is TH. So you plug that formula here. Now you're gonna find Q. Q is gonna be NCP times delta T. N again is from here, okay? CP is from 2 questions or 3 questions above, which is gamma times R divided by gamma minus 1, okay? That's what CP is. And TC, delta T is just T final minus T initial. That's easy, which is TC minus TH. Those are given. W in this case is going to be the difference of the two, or it's going to be equal to P, which is P min, times this volume V mid minus V max. Actually, I wrote it in here somewhere. Here it is, okay? So you probably need to include those equations again for gamma and all of that thing. Remember, CV is equal to R over gamma minus 1, and CP equals to gamma R over gamma minus 1, because that too you will need it. Those two equations are also needed for this process, okay? So you need CP and CV, and what else do we need? Okay, oops, what is this? Okay, never mind what that is. Anyway, so the point being in here is, this is, you can fill out the gap in here, and you check that delta U is equal to Q minus W, and it should be yes, okay? Of course, this is not a fillable, so you should be able to check it. Now you do the entropy. Entropy for this process, where is it? We said that it's I'm sorry, it's an nRTC divided by TC, so the TC canceled. No, I'm sorry, it's the log. It's going to be NCP, the natural log of the TC over TH. This is an isobaric process. Remember the tables from before, okay? Oh, my brain started to float all over the map, okay? This is this process. We're done with it. It's the second, when I say S mean, it's the adiabatic process. For the adiabatic process, Q is 0. So I know this is 0, okay? Because Q is 0. I mean, that's part of it. So delta U now. Delta U is going to be NCV delta T, where delta T is TH minus TC, and CV now is given by the other terms, and N is given by the other terms, and you're in good business, so you should be able to find it. Delta U, you should be able to also find it and express it. It should be minus this value, according to this convention. So it's in a similar fashion. This is NCV times delta T. N is given by this expression here. CV is given by this expression here. And delta T now is just TH minus TC. That's what TC is, and that's what TH is. TH is part of the entire isothermal. Okay. The last stage in here is at constant temperature. This cycle, this part of the cycle, this process. In that case, delta U is 0, so this should be 0, okay? Q should be equal to W according to the convention here. And whatever Q is, which is nRT, natural log of the final over the natural log of the initial, so you should be able to find these two expressions in here. Add all of these numbers, they should be 0. Add all of these numbers, they should add all of these numbers, I'm sorry, they should be your Q, your W net. Okay, and you check in here that indeed it checks. Qn should be part of this heat. This is your Qn. This is going to be positive. Q out should be this part of the system. So this should be Q out. This should be Qn. for this part. And of course, you're supposed to check to see if indeed it checks. It should check that the W net is the same as that one, as the difference between these two values. The efficiency of this engine, which is a W net over the Qn, it's going to be defined by 1 times the ratio of the temperatures. So they gave you that one. This is tau, the ratio of T hot over Tc, okay, over the log. So you don't have to worry about this part. Okay, it's given to you. Now, the second part now. Remember those numbers from the previous table? Table 2? We're going to plug in the numbers actually and tell me how many joules in here, how many joules in here, and all of these numbers in here. And you're going to find the efficiency now. Because you're going to plug in the value of tau. Remember, the value of tau is 1.33. So it's going to be 1 plus 1.33 minus 1 divided by 1.33 times the natural log of 1.33. Okay. And that is the calculations. It's lengthy, it's tedious, and it all starts from here and the stuff from the lab. So when I said the lab is a review for the exam, I was not really joking. This is really a review for the exam. Somebody was saying something? Was it Natasha who was saying something, or before I spoke up?
Oh no, I didn't say anything.
Okay. So you're supposed to go systematically. This is a good lab to work in teams, okay? This is actually an outstanding lab. So if you don't have a team member, please let me know, or let your classmates know so that you can get together and work on this. You don't have to meet, but at least working. Okay, I'm working on this engine and you're working on that engine, because you're supposed to submit 2 of them, not just 1, okay? And that helps because the other person is doing the calculations and you're reviewing it. And you do the calculation for the other one and the other one reviews it for you, okay? Because as you can see, you can clearly go wrong easily in one of the calculations that leads to a tremendous mistakes down the road, okay? So that is basically what this whole thing is. So this is a lab that must be done in teams. If you cannot find a team, please try very, very, very hard to work in teams so that you can have this lab done. And don't go all of you guys working on the same engine, because you are supposed to work on as many engines as possible to master these concepts and come to the exam with confidence to do any calculations you're confronted with. Sounds good?
Sounds good. I have a question about the exam. How many questions is it? Do you know?
Typically, usually you have 4 problems, okay?
Mm-hmm.
So that's how it is.
Okay.
Will it be
And you
open
will
the whole day?
I don't think so. I think it's going to be open from probably early in the morning till noon, till like 12:30 or something, during class time. So you should have enough time to do the exam and actually review it and work out whatever problems you have to upload it. And then that's it. Once you upload it and the time still did not expire, you see, you can still review it and upload it again if you want to, but that's it. Once you close it, that's it. You'll have only 1 attempt to it. So once you open Canvas for the exam, make sure you finish the exam before you close Canvas. Okay.
And is it open note, open book?
Yeah, for everybody except you, because I'm going to be there to make sure you don't. No, I'm joking.
Okay.
That sounds
For
fair.
What?
Okay, no. It's gonna be an open book, open everything. Okay, so you don't have to worry about that. You have to make sure you understand what you're doing. Make sure you're clear in your statements. And if you're gonna be, and this is a problem, okay, if you're gonna be handwriting stuff, make sure your handwriting is clear, and you take a nice picture of it. Try to lower the resolution of your phone, okay? Try not to use the highest resolution on your phone, because if you do that, and let's say, for example, there are 10 minutes left on the exam, and you take it with extreme high resolution, and you upload it, you will see that thing there, the hourglass going to upload thing, And before you upload the first problem, now the time has expired, which is a problem, okay? So try to lower the resolution a little on it in practice, okay? Practice doing this so that come exam time, you're not penalized for something that probably you should not be penalized for. And now, if you want to, you could use Word file, you could use whatever text editor that you have, but please, if you can, that's fine, upload it to PDF. Now, this is where it's going to be a problem, big time, okay? You're done with the exam, and you have it nicely working on your Google Drive, and you submit it from your Google Drive. Guess what? I will not be able to access your Google Drive. Okay? I don't have access to your Google will ask me to log in and to see if I have permissions from you to access your folder, and that is not how it's going to look. So download the stuff on your computer first, and then upload it to Canvas, because your exam is actually an official document that needs to be on college property, and Canvas is a college property. Google is not. So in other words, if there is an issue, for example, you think that it was not graded right or something, where is the reference? Where are we going to get to your exam? So do not use Google Drive or any online drive, and you try to give me the link to it. That's not going to work. So download it to your folder and then upload it. That's fine. Make sense?
Yep, makes sense.
Okay. So I know we took, yeah, we're supposed to end up in this time of the year anyway, so the lab, so, but you did not work on your lab. So we still have about, what is it, 40 minutes left or something. So if you guys want to hang around, that's fine. If you don't have teammates, this is a good time to ask for teammates. So I'm gonna stop the recording and let's get this thing going. So if you have team peers so that you work on this lab. So I'm going to stop the recording and communicate with one another to get your teams. And I know a lot of you do.
I have a question.
Yes.
This is on lab 3. I was wondering for the gamma, like, how are we supposed to plug in the, like, I found the equation from the angular frequency, but like, I don't know how to like plug it back in so I can find the gamma value, if that makes sense.
If you once you have the data, you can use Excel. We do a graph using Excel. Are you familiar with that approach or not?
No, I'm not. Sorry.
Okay, let's have a one-on-one session,
All right.
and then through that example. And if anybody else interested, we can probably have a meeting this coming, maybe, what is today, Thursday, maybe tomorrow morning or something.
At what time?
Around 9 a.m.
I have another meeting at that time too. Sorry.
Okay, so we'll probably then you let me know when it's convenient, and then we can record this for the benefit of everybody else, okay?
You don't have time right now, if that's okay, or?
Okay, so let's first of all, we have to end this session then and start a new one, because I want the recording later on to go on campus, okay?
Yeah, that's fine.
Professor, I have one last question.
Yes, Helen.
So what was the discussion question again? It was restate the second law of what?
Second law. We have only one, okay?
The second law of thermodynamics?
Yes, like a second law of thermodynamics. There are 3 different ways of putting it. And then also to finish that efficiency of that engine from problem 2047 and make sure that that efficiency, had it been a Carnot, is more than 0.611. Okay?
Okay.
Okay, so let me stop the recording. And I'll have to end that. Natasha, I know you want to meet, so probably I'm going to send you a separate link for another session, okay?
All
Sounds
right.
good?
Yep.
Okay.
Have a good day,
So
Professor.
okay, you too, guys. Thank you.